If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. What defines immensity in a universe so vast it defies human comprehension? When we gaze at the night sky, the stars appear like pinpricks of light on an endless canvas, each one a reminder of something far greater than our planet, our solar system, or even our galaxy. But when astronomers refer to the largest structures in the universe, they are speaking of phenomena so immense that even light, the fastest thing in the cosmos, can take billions of years to traverse them. The journey into understanding cosmic immensity begins with a concept: scale. Humans exist on a scale defined by everyday experiences, meters, kilometers, and occasionally light years for the most adventurous thinkers. However, these measurements quickly become insufficient when applied to the structures of the cosmos. Imagine the Earth, a sphere approximately 12,742 kilometers in diameter, as a tiny speck orbiting the Sun, which is over 100 times larger. Beyond that, the Sun itself is just one star among hundreds of billions in the Milky Way galaxy, which stretches across 100,000 light-years. Yet, even the Milky Way is but a mere grain of sand in a vast ocean of galaxies. The true challenge in defining biggest lies in understanding how the universe organizes itself. On the smallest scales, atoms combine to form molecules, which then form stars, planets, and eventually galaxies. Galaxies, however, rarely exist alone. They cluster together, pulled by the force of gravity into vast assemblies, merging, interacting, and forming galactic superclusters. These superclusters, in turn, are linked by a network of filaments composed of galaxies and dark matter, creating what we call the cosmic web, the universe's skeleton. The boundaries of these structures are so vast that they challenge not only measurement but also perception. For astronomers, defining the size of a structure depends on criteria like gravitational coherence, density, and spatial connectivity. Is a galaxy cluster defined solely by the galaxies within it? Or do the intergalactic gases, dark matter halos, and filaments also count? The answer, it seems, varies depending on the perspective. At the heart of measuring these structures is the principle of light travel time. When we observe distant objects, we are seeing them as they were billions of years ago, their light having traveled across unimaginable expanses to reach us. This delay creates a window into the past, allowing us to see not only distant galaxies, but also the imprint of the universe's earliest moments. Structures such as the Sloan Great Wall or the Hercules Corona Borealis Great Wall are not just large. They are ancient, existing at a time when the universe was still shaping itself into the cosmic web we observe today. But what is the largest thing we can conceptualize in the observable universe? To answer this, we must grapple with the limitations of observation itself. The observable universe, with a radius of approximately 46.5 billion light-years, is defined by the distance light has traveled since the Big Bang. Beyond this boundary lies the unobservable, a realm that could contain even grander structures, but remains forever hidden from view due to the finite speed of light and the universe's continual expansion. In contemplating the largest structures, we must also account for the forces that govern their formation. Gravity, the cosmic architect, pulls matter into dense regions, forming galaxies, clusters, and superclusters. However, countering gravity is dark energy, an enigmatic force driving the universe's accelerated expansion. The tension between these two forces not only shapes the present universe, but also determines its ultimate fate. As dark energy continues to dominate, the largest structures may one day drift apart, leaving behind isolated islands of matter in a sea of nothingness. Even within these incomprehensible scales, there is beauty in the patterns and connectivity of the cosmos. The cosmic web, for instance, resembles the neural networks of a brain, with filaments and nodes linking clusters of matter. This interconnectedness is not merely aesthetic. It represents the underlying physics of the universe, where dark matter forms the scaffolding and baryonic matter, the stars and galaxies we can see, illuminates its framework. As we venture further into this exploration, the concept of biggest takes on new dimensions. It is not merely about size, but also about influence, age, and the profound interconnectedness that binds the universe together. The Hercules Corona Borealis Great Wall, the largest observed structure, stretches across 10 billion light-years, dwarfing our imagination and challenging the very definitions of structure. Yet even this gargantuan formation is just one thread in the larger tapestry of the universe. With these ideas in mind, we begin our journey into the largest structures in the cosmos, a voyage that will take us from the filaments of the cosmic web to the emptiest voids and beyond. Each step will reveal a deeper understanding of how the universe constructs its vast hierarchy, inviting us to reconsider what it means to exist within such an extraordinary expanse. When scientists first began mapping the universe on a large scale, they envisioned it as a random scattering of galaxies, an almost chaotic arrangement with no discernible order. However, as observations improved, a pattern emerged, a grand cosmic design that resembled an intricate web stretching across the universe. This vast, interconnected structure, known as the cosmic web, forms the backbone of the cosmos, connecting galaxies, clusters, and superclusters through immense filaments of matter. The cosmic web's discovery is a story of technological advancement and scientific curiosity. In the 1980s, astronomers conducting redshift surveys began to notice something unexpected. Galaxies were not distributed evenly throughout space, but instead appeared to cluster along thin, thread-like structures. Between these threads were enormous empty regions, known as voids. It was as if the universe had woven itself into a three-dimensional tapestry, with matter concentrated in strands and nodes, leaving vast expanses of emptiness. To understand how the cosmic web came to be, we must journey back to the beginning of time, to the aftermath of the Big Bang. In its earliest moments, the universe was a nearly uniform soup of energy and matter. However, slight irregularities in this primordial mix, tiny fluctuations in density, created the seeds of structure. These fluctuations, amplified by the force of gravity, drew matter together over billions of years, forming the filaments, nodes, and voids we observe today. The cosmic web's filaments are its most striking feature. Stretching across hundreds of millions of light years, these filaments are composed of galaxies, gas, and dark matter. They serve as the highways of the universe, funneling material into larger structures like galaxy clusters and superclusters. Despite their immense scale, these filaments are incredibly faint. Much of their mass lies in the form of dark matter, an invisible substance that interacts with ordinary matter only through gravity. This dark matter forms the scaffolding upon which the visible universe is built, shaping the distribution of galaxies and stars. At the intersections of filaments lie the nodes of the cosmic web. These nodes are home to galaxy clusters, dense regions teeming with hundreds or even thousands of galaxies. The gravitational pull of these clusters is so strong that it bends light, creating phenomena like gravitational lensing. By studying these distortions, astronomers can map the distribution of dark matter within the nodes and gain insights into the web structure. The cosmic web is not static, it is constantly evolving. Over billions of years, matter flows along the filaments, feeding the growth of clusters and superclusters. This movement is driven by gravity, which pulls material into denser regions. However, the expansion of the universe, driven by dark energy, opposes this gravitational pull. As a result, the web's growth is slowing, and in the distant future, its structures may become frozen in time, their development halted by the relentless expansion of space. One of the most intriguing aspects of the cosmic web is its resemblance to structures at vastly different scales. For example, the arrangement of galaxies in the web bears a striking similarity to the neural networks of a brain, with filaments and nodes connecting regions of high activity. This parallel raises profound questions about the nature of complexity and organization in the universe. Is the cosmic web merely a coincidence of physics, or does it reflect a deeper, underlying principle of structure in nature? To map the cosmic web, astronomers use a variety of techniques. Large-scale galaxy surveys, such as the Sloan Digital Sky Survey, provide detailed maps of galaxy positions, revealing the web's filamentary structure. Meanwhile, observations of the cosmic microwave background, the faint afterglow of the Big Bang, offer clues about the web's origins, showing how the universe's initial fluctuations grew into the intricate patterns we see today. Despite these advances, much of the cosmic web remains hidden. The filaments, in particular, are challenging to study because they are dominated by dark matter and contain only trace amounts of visible gas and galaxies. New methods, such as using fast radio bursts to probe the distribution of matter, are helping to unveil these elusive structures. These bursts, which are short, intense flashes of radio waves, interact with the material they pass through, providing valuable information about the density and composition of the filaments. The voids of the cosmic web are equally fascinating. These vast, empty regions, some spanning hundreds of millions of light years, are among the universe's most mysterious features. They are not entirely devoid of matter, but contain only a sparse sprinkling of galaxies and gas. Studying these voids can provide insights into the universe's expansion and the nature of dark energy. In many ways, the voids are as important as the filaments, representing the other half of the cosmic dance between matter and emptiness. The cosmic web also plays a crucial role in shaping the lives of galaxies. Galaxies within filaments and clusters experience a very different environment than those in voids. For example, galaxies in dense regions are more likely to interact and merge, leading to the formation of larger galaxies. Meanwhile, isolated galaxies in voids evolve more slowly, free from the gravitational influences of neighbors. As we peer deeper into the cosmic web, we begin to see it not just as a framework, but as a dynamic, interconnected system. The web is a testament to the power of gravity and the interplay between matter and energy. It is a reminder of the universe's grand scale and the delicate balance of forces that have shaped its evolution. The cosmic web invites us to think about the universe in a new way. It is not merely a collection of galaxies scattered across space, but a vast, living structure with filaments and nodes connecting the farthest reaches of the cosmos. As our understanding of the web grows, so too does our appreciation for the intricate beauty of the universe, a beauty that lies not just in its individual parts, but in the profound connections that bind them together. Among the largest and most striking formations in the universe are galaxy clusters, the massive swarms of galaxies that represent the densest regions of the cosmic web. These colossal assemblies are held together by gravity, housing hundreds or even thousands of galaxies along with vast amounts of dark matter and hot gas. As one of the universe's fundamental building blocks, galaxy clusters provide a unique window into the dynamics of large-scale structures and the forces shaping the cosmos. Galaxy clusters are not merely collections of galaxies. They are dynamic, living systems. At their cores, galaxies interact in a dance of gravitational pulls, occasionally colliding and merging to form even larger galaxies. Surrounding these clusters is a halo of dark matter, which forms the gravitational glue binding the cluster together. In addition to galaxies and dark matter, galaxy clusters are filled with hot, X-ray emitting gas that forms a diffuse medium known as the intracluster medium, ICM. This hot gas, heated to tens of millions of degrees, represents a major component of the cluster's total mass. The discovery of galaxy clusters dates back to the early 20th century, when astronomers first noticed dense groupings of galaxies in their observations. One of the most famous examples is the Virgo cluster, located about 54 million light-years away and home to thousands of galaxies, including several massive elliptical galaxies. Closer to Earth, the Local Group, which includes the Milky Way, Andromeda, and about 50 other galaxies, is part of a much larger structure known as the Laniakea supercluster. The formation of galaxy clusters began early in the universe's history, shortly after the Big Bang. As matter coalesced under the influence of gravity, small fluctuations in density grew into the seeds of larger structures. Over billions of years, these seeds evolved into clusters, drawing in galaxies and dark matter along the filaments of the cosmic web. The result is a diverse population of clusters, each with its unique characteristics and history. One of the defining features of galaxy clusters is their immense gravitational influence. This gravity not only binds the cluster's components together, but also affects the surrounding space, bending light in a phenomenon known as gravitational lensing. By studying these lenses, astronomers can map the distribution of dark matter within clusters, revealing their hidden structure. In some cases, the light from background galaxies is magnified and distorted into arcs and rings, providing spectacular visual evidence of the cluster's gravitational power. The largest galaxy clusters are sometimes referred to as giant ellipticals, due to the enormous elliptical galaxies often found at their centers. These central galaxies, such as M87 in the Virgo cluster, are the result of repeated mergers and interactions. Over time, smaller galaxies fall into the cluster, merging with the central galaxy and adding to its mass. This process of hierarchical growth is one of the key mechanisms driving the evolution of clusters. The interactions within galaxy clusters are not always gentle. Galaxies within clusters can experience tidal forces, stripping them of gas and stars, and leaving behind streams of material that enrich the intracluster medium. This process, known as ram pressure stripping, plays a crucial role in galaxy evolution. Galaxies that lose their gas often become quenched, ceasing to form new stars. This explains why clusters are often dominated by older, redder galaxies, contrasting with the star-forming spirals found in less dense regions. The hot gas in the intracluster medium also provides critical insights into the physics of galaxy clusters. This gas emits X-rays, allowing astronomers to study its temperature, density, and distribution. Observations of the ICM reveal that galaxy clusters are not static but rather dynamic systems. Shock waves and turbulence, generated by mergers and collisions between smaller clusters, ripple through the intracluster medium, creating intricate patterns of hot and cold gas. One of the most dramatic examples of cluster activity is the phenomenon of cluster mergers. When two galaxy clusters collide, their dark matter halos pass through each other relatively unimpeded, while their hot gas interacts, creating massive shock fronts. The Bullet cluster is a famous example, showcasing the separation of dark matter and normal matter in the aftermath of a collision. These events provide compelling evidence for the existence of dark matter, as the gravitational effects observed do not match the distribution of visible matter alone. Despite their massive size and gravitational pull, galaxy clusters are still subject to the universe's expansion. Over time, as dark energy drives the accelerated expansion of the cosmos, clusters will become increasingly isolated from one another. This expansion also limits the growth of new clusters, as the flow of matter along the filaments slows and eventually halts. In the far future, galaxy clusters may remain as lonely islands of matter in an ever-expanding sea of space. Galaxy clusters also play a crucial role in shaping the larger structures of the universe. Connected by filaments of the cosmic web, they act as hubs of activity, influencing the flow of gas, stars, and dark matter. The interplay between clusters and their surroundings is a dynamic process, with material constantly moving in and out. For instance, clusters can accrete galaxies and gas from the surrounding filaments, growing over time. Conversely, they can expel material through powerful outflows driven by supermassive black holes at the centers of their largest galaxies. The study of galaxy clusters continues to evolve, with new discoveries shedding light on their complexity and diversity. Advances in technology, such as space-based X-ray telescopes and ground-based surveys, have allowed astronomers to map clusters in unprecedented detail. Additionally, simulations of cluster formation, powered by supercomputers, provide valuable insights into their origins and evolution. Ultimately, galaxy clusters represent a microcosm of the universe itself. They embody the interplay of matter, energy, and gravity on a colossal scale, serving as laboratories for studying the fundamental forces that shape the cosmos. From their dramatic mergers to their serene cores, these clusters reveal the beauty and complexity of the universe's largest structures, inviting us to explore their mysteries and uncover the secrets of their immense power. If galaxy clusters are the bustling cities of the cosmic web, then superclusters are the vast nations that connect them. These immense structures, composed of multiple galaxy clusters linked by filaments of galaxies and dark matter, are among the most colossal formations in the observable universe. Superclusters are not just collections of galaxies. They are cosmic giants that illustrate the universe's complex hierarchy and interconnected nature. A supercluster is essentially a large group of galaxy clusters that are gravitationally associated. These structures span hundreds of millions of light years, dwarfing individual clusters in size and complexity. Among the most famous superclusters is Laniakea, our home supercluster. Discovered in 2014, Laniakea encompasses the Virgo cluster, which includes the Milky Way and extends over 500 million light years. Its name, meaning immeasurable heaven in Hawaiian, is a fitting tribute to its monumental scale. The history of superclusters begins with the formation of the cosmic web itself. In the early universe, small fluctuations in density grew under the influence of gravity, forming filaments and nodes. As matter flowed along these filaments, it accumulated in dense regions, giving rise to clusters and superclusters. However, the growth of these structures is not infinite. The accelerated expansion of the universe, driven by dark energy, is gradually pulling clusters and superclusters apart, ensuring that their formation is a story of the distant past. Superclusters come in various shapes and configurations. Some, like the Shapley supercluster, are incredibly dense, containing dozens of clusters within a relatively compact area. The Shapley supercluster, located 650 million light-years away, is one of the most massive known superclusters, with a mass over 10 million billion times that of the Sun. Others, like Pisces Cetus, are more sprawling, with clusters and galaxies connected by long, thin filaments. The sheer size of superclusters presents a challenge in defining their boundaries. Unlike galaxy clusters, which are gravitationally bound systems, superclusters are only loosely held together by gravity. This means that the galaxies and clusters within a supercluster are not necessarily moving toward a common center, but instead share a general region of space. To identify and classify superclusters, astronomers use measurements of galaxy redshifts, which indicate their velocities and distances, and map their positions in three-dimensional space. One of the most intriguing aspects of superclusters is their role in shaping the flow of galaxies and matter. Superclusters act as gravitational wells, influencing the movement of material across vast distances. The Great Attractor, a region of intense gravitational pull within Laniakea, is a prime example of this influence. Galaxies, including our own, are moving toward this region at speeds of hundreds of kilometers per second, drawn by its immense mass. Despite their incredible size, superclusters are far from uniform. Within their boundaries, they contain regions of varying density, from dense clusters to sparsely populated filaments and voids. This variation is a testament to the dynamic processes that shape these structures, including galaxy mergers, cluster collisions, and the influence of dark matter. Superclusters also provide valuable clues about the universe's large-scale structure, offering a snapshot of how matter is distributed on the grandest scales. The study of superclusters has been revolutionized by large-scale galaxy surveys. Projects like the Sloan Digital Sky Survey, SDSS, and the 2-Micron All-Sky Survey, 2MASS, have mapped millions of galaxies, revealing the intricate patterns of clusters, filaments, and voids that define superclusters. These surveys have also uncovered new superclusters, some of which are so large that they challenge our understanding of cosmic evolution. For example, the Sarasvati supercluster, discovered in 2017, spans over 600 million light-years and contains thousands of galaxies. Superclusters are not just impressive for their size. They also play a critical role in understanding the universe's history and fate. By studying their distribution and properties, astronomers can test theories of cosmic evolution, including the influence of dark energy and the nature of dark matter. Superclusters also serve as natural laboratories for studying galaxy evolution, as the dense environments within them can accelerate processes like star formation and mergers. One of the most fascinating questions about superclusters is whether they are the largest structures in the universe. While superclusters represent the upper end of known gravitationally influenced systems, even larger patterns, such as the Hercules Corona Borealis Great Wall, exist. These structures blur the line between superclusters and other formations, raising questions about how to define and categorize the universe's largest features. Superclusters also inspire profound philosophical questions. Their existence reminds us of the incredible scales at which the universe operates, stretching the limits of human imagination. At the same time, their interconnectedness highlights the unity of the cosmos, where even the largest structures are part of a grander, cohesive whole. As the universe continues to expand, the fate of superclusters is sealed. Over billions of years, dark energy will drive their constituent clusters and galaxies apart, leaving behind isolated pockets of matter. In the distant future, superclusters may no longer be recognizable as distinct entities, their components scattered across an ever-expanding void. Yet, their legacy will remain, imprinted in the structure of the cosmic web and the galaxies they shaped. Superclusters are a testament to the universe's complexity and majesty. They are not merely collections of galaxies and clusters, but dynamic systems that reveal the interplay of matter, energy, and gravity on an unimaginable scale. As we delve deeper into their mysteries, we gain not only a greater understanding of the cosmos, but also a profound appreciation for the beauty and grandeur of the universe. In the grand tapestry of the universe, where galaxies, clusters, and superclusters weave an intricate web, there are regions that defy this pattern. Immense, yawning expanses known as voids. These vast, almost empty spaces are some of the largest features in the cosmos, spanning hundreds of millions of light years and containing very little matter. Yet, their emptiness holds profound significance, shaping the overall structure of the universe and providing critical insights into its evolution. Void regions are defined by their low density compared to the average distribution of matter in the universe. While the dense nodes and filaments of the cosmic web teem with galaxies, stars, and gas, voids are nearly barren, with only a few faint galaxies scattered throughout. They are so sparse that their matter content is often less than 1/10 the cosmic average. Despite this, voids are far from irrelevant. They play a crucial role in balancing the universe's large-scale structure and influencing the motion of galaxies and matter. The discovery of voids dates back to the late 20th century, when astronomers conducting large-scale galaxy surveys began to notice gaps in the distribution of galaxies. One of the first voids to be identified was the Boötes void, an enormous region located about 700 million light-years away. Spanning approximately 330 million light-years in diameter, the Boötes void contains fewer than 60 known galaxies, earning it the nickname the Great Nothing. The origins of cosmic voids can be traced to the early universe. Shortly after the Big Bang, the universe was nearly uniform, with only slight density fluctuations. Over time, gravity pulled matter from less dense regions into denser ones, forming the filaments and clusters of the cosmic web. The regions left behind became voids, expanding as matter flowed outward and the universe itself grew larger. Today, voids account for a significant portion of the universe's volume, with some estimates suggesting that they make up over 80% of the observable cosmos. Voids are not entirely devoid of matter. They contain trace amounts of gas, as well as a small number of galaxies, often arranged in thin sheets or filaments at their edges. These galaxies, known as void galaxies, are fascinating in their own right. Isolated from the dense environments of clusters, they experience minimal gravitational interactions and often retain their original gas content. As a result, void galaxies tend to be blue, star-forming spirals, in stark contrast to the red, quenched galaxies found in clusters. The study of voids has revealed intriguing properties that challenge our understanding of the universe. For instance, voids are not perfectly spherical. Instead, they exhibit irregular shapes influenced by the distribution of surrounding matter. Their growth is driven by the universe's expansion, which causes them to stretch and merge over time, creating larger and more complex voids. This process, sometimes called void merging, reflects the dynamic nature of the cosmic web, where matter continuously flows and rearranges itself. Voids also affect the behavior of light and matter in surprising ways. When light from distant galaxies passes through a void, it experiences a phenomenon known as the integrated Sachs-Wolf effect. This effect occurs because the gravitational potential of a void changes as the universe expands, causing a subtle shift in the energy of photons passing through it. By studying these shifts, astronomers can learn more about the properties of dark energy and the universe's expansion. Perhaps the most significant role of voids lies in their potential to probe the mysteries of dark energy. The accelerated expansion of the universe, attributed to dark energy, influences the growth of voids by stretching them and altering their shapes. By studying the size, distribution, and evolution of voids, astronomers can test theories of dark energy and refine models of cosmic evolution. Voids are, in essence, natural laboratories for exploring the universe's most enigmatic force. The boundaries of voids, where they meet the dense regions of the cosmic web, are sites of intriguing interactions. These boundaries often feature walls and filaments of galaxies, which act as the dividing lines between emptiness and density. The interplay between these regions can create fascinating phenomena, such as the motion of galaxies along filamentary paths or the accumulation of gas at void edges. These dynamics offer valuable insights into the forces shaping the universe on large scales. Despite their vastness, voids remain one of the least explored aspects of the cosmos. Observing these empty regions is inherently challenging, as their sparse contents emit little light. However, advances in technology and methodology are opening new avenues for studying voids. Techniques such as void stacking, which combines data from multiple voids to enhance their signal, and the use of fast radio bursts to trace void matter, are helping astronomers unravel their mysteries. Voids also raise profound questions about the nature of the universe. Why is the cosmos structured in such a way that voids occupy so much of its volume? What role do they play in the universe's overall balance? And could there be patterns within their emptiness that we have yet to discover? These questions highlight the importance of voids not as mere gaps in the cosmic web, but as essential components of the universe's architecture. In the future, voids may become even more prominent as the universe continues to expand. Over billions of years, the flow of matter into filaments and clusters will slow, and voids will grow larger and emptier. Eventually, they may dominate the universe's structure, with isolated galaxies and clusters surrounded by vast stretches of nothingness. This distant future underscores the dynamic nature of voids, which, despite their emptiness, are constantly evolving. Voids are paradoxical, vast and empty, yet rich in significance. They represent the other side of the cosmic coin, balancing the dense regions of the universe and shaping its overall structure. By studying these vast cosmic deserts, we not only deepen our understanding of the universe's large-scale organization, but also confront the profound questions of existence itself. Why is there something, and why is there so much nothing? In the vast reaches of the universe, beyond the intricate patterns of galaxies and clusters, there exist structures so immense that they redefine our understanding of scale. Great walls. These cosmic chains, composed of interconnected galaxies, clusters, and superclusters, are the largest coherent structures in the observable universe. Stretching across hundreds of millions of light-years, they form the backbone of the cosmic web, bridging the densest regions of matter in the cosmos. The term Great Wall was first coined in the late 20th century, when astronomers conducting large-scale galaxy surveys stumbled upon a stunning discovery. In 1989, Margaret Geller and John Huckera revealed the existence of the CFA-2 Great Wall, a structure spanning over 500 million light-years. This discovery was groundbreaking, providing the first glimpse of the universe's large-scale organization beyond clusters and superclusters. However, the CFA-2 Great Wall was only the beginning. Subsequent surveys uncovered even larger structures, each one challenging previous conceptions of size and connectivity. Among these are the Sloan Great Wall, stretching approximately 1.37 billion light-years, and the Hercules Corona Borealis Great Wall, the largest known structure in the universe, extending a staggering 10 billion light-years. These colossal formations blur the line between individual superclusters, revealing the intricate and interconnected nature of the cosmic web. The formation of great walls is deeply tied to the universe's early history. Shortly after the Big Bang, small fluctuations in the density of matter began to grow under the influence of gravity. Over billions of years, these fluctuations evolved into the large-scale structures we see today. Great walls represent the densest and most connected regions of this process, where gravity has drawn together massive amounts of matter along the filaments of the cosmic web. The structure of great walls is both complex and awe-inspiring. They are not solid entities but are composed of countless galaxies, clusters, and superclusters linked by filaments of dark matter and gas. These filaments act as cosmic highways, funneling material into the dense regions of the walls. At the intersections of these filaments lie the nodes of the cosmic web, where galaxy clusters and superclusters converge. The result is a network of interconnected regions, with great walls serving as the most prominent features. The discovery and study of great walls have relied on cutting-edge technology and extensive surveys. Projects like the Sloan Digital Sky Survey (SDSS) have mapped millions of galaxies, revealing the large-scale structure of the universe in unprecedented detail. By analyzing the positions and velocities of galaxies, astronomers can reconstruct the three-dimensional layout of the cosmos, identifying the massive chains and walls that span its expanse. One of the most intriguing aspects of great walls is their apparent defiance of the cosmological principle, which states that the universe is homogeneous and isotropic on the largest scales. While this principle holds true on scales above a few billion light-years, the existence of structures like the Hercules Corona Borealis Great Wall suggests that the universe may not be as uniform as once thought. This raises profound questions about the underlying physics governing the cosmos and challenges current models of cosmic evolution. The gravitational influence of great walls extends far beyond their visible components. These structures are dominated by dark matter, which acts as the invisible framework upon which galaxies and clusters are built. By studying the motion of galaxies within and around great walls, astronomers can infer the distribution of dark matter and better understand its role in shaping the universe's largest structures. Great walls also have a significant impact on the flow of matter and energy in the cosmos. They act as barriers and conduits, redirecting the movement of galaxies, gas, and even radiation. For example, the presence of a great wall can create gravitational lensing effects, bending and magnifying light from background objects. These effects provide valuable tools for studying both the walls themselves and the distant universe beyond. Despite their immense scale, great walls are not static. Over billions of years, they evolve as matter flows along filaments and accumulates in dense regions. However, the accelerated expansion of the universe, driven by dark energy, is gradually halting this process. As space stretches, the flow of matter slows, and the growth of great walls diminishes. In the distant future, these structures may become relics of a more dynamic cosmic era. The study of great walls has also uncovered fascinating patterns and alignments. For instance, some galaxies within walls exhibit a tendency to align their rotation axes with the filaments they inhabit. This phenomenon, known as cosmic alignment, suggests that the formation of galaxies and their orientation is influenced by the large-scale structure of the universe. These alignments provide clues about the physics of galaxy formation and the interplay between dark matter, gas, and gravity. As we continue to map the universe and uncover new great walls, we are reminded of the sheer scale and complexity of the cosmos. These structures, spanning billions of light years, challenge our understanding of what it means to be big. They also inspire profound philosophical questions about the nature of the universe. Are great walls the largest structures we will ever observe? Or do even larger formations exist beyond our cosmic horizon? How do these structures fit into the grand design of the cosmos? And what do they reveal about its origins and future? Great walls are more than just monumental structures. They are the culmination of billions of years of cosmic evolution. They represent the intricate interplay of matter, gravity, and time, forming the backbone of the universe's large-scale architecture. As we delve deeper into their mysteries, we uncover not only the secrets of the cosmos, but also the awe-inspiring beauty of its design. Among the vast and intricate structures of the universe, one stands as the largest ever discovered: the Hercules Corona Borealis Great Wall. Spanning an incomprehensible 10 billion light-years across, this colossal cosmic chain challenges everything we thought we knew about the size and limits of the observable universe. Its discovery has left astronomers and cosmologists awestruck, raising profound questions about the nature of the cosmos and its fundamental principles. The Hercules Corona Borealis Great Wall was first identified in 2013 during a study of gamma-ray bursts, GRBs. These bursts, the most energetic explosions in the universe, often occur when massive stars collapse or neutron stars collide, emitting intense radiation visible across vast distances. By mapping the locations of GRBs, astronomers can trace the distribution of matter in the universe, as GRBs are typically associated with star-forming galaxies. What researchers found was extraordinary. A concentrated region of GRBs spread over 10 billion light-years, indicating an immense structure of galaxies and clusters linked by filaments. This structure dwarfed previous record holders, such as the Sloan Great Wall and the CFA2 Great Wall, by orders of magnitude. Located in the direction of the Hercules and Corona Borealis constellations, it was appropriately named the Hercules Corona Borealis Great Wall. To put its size into perspective, the Hercules Corona Borealis Great Wall spans roughly 10% of the observable universe's diameter. Light, traveling at 300,000 kilometers per second, would take 10 billion years to traverse its length. This means that when we observe this structure, we are looking at it as it existed billions of years ago, during an era when the universe was less than half its current age. The discovery of this Great Wall has profound implications for our understanding of the universe. According to the cosmological principle, the universe should appear homogeneous and isotropic on the largest scales, meaning its structure should be uniform no matter where or how we observe it. However, the existence of such a massive and coherent structure challenges this principle. If the universe can organize itself on scales as vast as 10 billion light-years, are there even larger structures yet to be discovered? And what does this mean for our models of cosmic evolution? The formation of the Hercules Corona Borealis Great Wall is a mystery. The universe is approximately 13.8 billion years old, and large-scale structures require significant time to form as gravity pulls matter together. For a structure of this size to exist, its components would have needed to begin clustering very early in cosmic history. This raises questions about the role of dark matter and dark energy in shaping such immense formations. Could unknown forces or phenomena have influenced its creation? The structure's impact on the surrounding universe is equally significant. The immense gravitational pull of the Hercules Corona Borealis Great Wall affects the motion of nearby galaxies and clusters, drawing them into its influence. Its presence also affects the flow of radiation and particles across space, creating subtle distortions that astronomers can detect. These effects help researchers study the wall's composition and map its extent with greater precision. The discovery of the Hercules Corona Borealis Great Wall also underscores the importance of gamma-ray bursts as a tool for understanding the universe's large-scale structure. Unlike visible light, which can be absorbed or scattered by dust and gas, gamma rays travel relatively unimpeded, providing a clearer view of distant regions. By analyzing the distribution of GRBs, astronomers can uncover patterns that reveal the underlying cosmic web, even in regions where traditional surveys struggle. Despite its immense size, the Hercules Corona Borealis Great Wall remains elusive. Much of it lies at the edge of the observable universe, where the expansion of space and the dimming of light make observations increasingly challenging. Future telescopes, capable of detecting fainter and more distant objects, will be crucial for studying this structure in greater detail. Additionally, advances in simulation and modeling will help researchers understand how such a vast formation could arise within the constraints of current cosmological theories. The implications of this discovery extend beyond astronomy. The existence of the Hercules Corona Borealis Great Wall prompts us to reconsider our place in the universe. If structures of this magnitude exist, what does that say about the scale of the cosmos? Could there be similar or even larger formations beyond the limits of our observation? And what might this mean for our understanding of the universe's origins and fate? Philosophically, the Hercules Corona Borealis Great Wall serves as a reminder of the universe's staggering complexity and vastness. It is a testament to the power of gravity and the interplay of matter and energy on the grandest scales. Yet, it also highlights the limitations of human perception. As we probe deeper into the cosmos, We are continually confronted with structures and phenomena that challenge our understanding, forcing us to expand our horizons and embrace the unknown. In the end, the Hercules Corona Borealis Great Wall is more than just a record holder. It is a symbol of the universe's boundless creativity, a structure so vast and intricate that it defies easy explanation. As we continue to study it, we gain not only a deeper appreciation for the cosmos, but also a renewed sense of wonder at its infinite possibilities. The universe we see, the stars, galaxies, and cosmic structures glowing across vast distances, is only a fraction of what exists. Beneath the luminous fabric of the cosmos lies an invisible but dominant force: dark matter. This mysterious substance is the silent architect of the universe's largest structures, from galaxy clusters to the immense filaments of the cosmic web. Without dark matter, the universe as we know it could not exist. Dark matter makes up approximately 27% of the universe's total mass energy content, far outweighing the mere 5% composed of ordinary, baryonic matter, the stuff of stars, planets, and people. Despite its prevalence, dark matter remains elusive, as it does not emit, absorb, or reflect light. Its presence is inferred through its gravitational effects on visible matter, light, and the large-scale structure of the universe. The role of dark matter in shaping the cosmos began shortly after the Big Bang. In the universe's earliest moments, dark matter clumped together under the influence of gravity, forming dense regions known as dark matter halos. These halos served as the scaffolding for the formation of galaxies and larger structures. Without the gravitational pull of dark matter, the gas and dust that form stars and galaxies would have remained too diffuse to coalesce. On the largest scales, dark matter dictates the distribution of the cosmic web. Simulations of the universe's evolution, such as the famous Millennium Simulation, reveal how dark matter forms a vast network of filaments and nodes, with galaxies and clusters tracing its invisible framework. These simulations show that the universe's large-scale structure is remarkably consistent with the presence of dark matter, providing strong evidence for its existence. One of dark matter's most critical roles is in the formation and stability of galaxy clusters. These clusters, the densest regions of the cosmic web, are held together by the immense gravitational pull of dark matter. Observations of galaxy clusters, such as the Bullet Cluster, have provided direct evidence of dark matter's presence. In the Bullet Cluster, the visible matter, hot gas, and dark matter have been separated by a collision, with the latter detected through its gravitational effects on background light, a phenomenon known as gravitational lensing. Gravitational lensing is one of the most powerful tools for studying dark matter. When light from distant galaxies passes near a massive object, such as a dark matter halo, it is bent and magnified, creating arcs and distortions. By analyzing these distortions, astronomers can map the distribution of dark matter, revealing its role in shaping galaxies, clusters, and larger structures. These maps show that dark matter dominates the mass of most large-scale cosmic formations, often outstripping visible matter by a factor of 5 or more. Dark matter also influences the dynamics of galaxies within clusters and superclusters. Without the additional mass provided by dark matter, galaxies would not orbit their clusters as quickly as they do. Observations of galaxy rotation curves, plots of rotational velocity versus distance from the center, further support this. The outer regions of galaxies rotate faster than can be explained by visible matter alone, indicating the presence of an unseen mass. On the scale of superclusters and great walls, dark matter's influence becomes even more pronounced. These colossal structures are interconnected by filaments of dark matter, which act as cosmic highways, funneling galaxies and gas into denser regions. As matter flows along these filaments, it forms the dense nodes and walls that define the cosmic web. The Hercules Corona Borealis Great Wall, for example, is likely underpinned by an immense network of dark matter, providing the gravitational foundation for its vast size and coherence. The study of dark matter has also revealed intriguing patterns in the alignment of galaxies and their host structures. For instance, galaxies within filaments often exhibit a preferred orientation, with their spin axes aligned along the filament. This phenomenon, known as cosmic alignment, suggests that dark matter filaments influence the angular momentum of galaxies as they form and evolve. These alignments provide additional evidence of dark matter's pervasive role in shaping the universe. Despite its critical importance, the nature of dark matter remains one of the greatest mysteries in physics. Numerous theories have been proposed to explain its composition, from weakly interacting massive particles, WIMPs, to axions and sterile neutrinos. Experiments on Earth, such as those conducted in underground detectors and particle accelerators, are searching for direct evidence of dark matter particles. But so far, none have been conclusively detected. Another mystery surrounding dark matter is how it interacts, or doesn't, with ordinary matter and itself. Dark matter is thought to interact primarily through gravity, but some theories suggest it may have weak self-interactions that could affect the structure of galaxies and clusters. Observations of certain cosmic phenomena, such as the density profiles of dark matter halos, provide clues about these interactions, but much remains unknown. As the universe continues to expand, dark matter's role is evolving. In the early universe, dark matter was the dominant force driving the growth of structure, pulling matter together to form galaxies, clusters, and superclusters. Today, however, the influence of dark energy, which drives the universe's accelerated expansion, is becoming more significant. Over time, dark energy will outpace dark matter, halting the growth of large-scale structures and isolating galaxies from one another. Despite these challenges, the study of dark matter is advancing rapidly. New observations, simulations, and experiments are providing deeper insights into its properties and effects. Projects like the Vera C. Rubin Observatory and the Euclid Space Telescope are poised to revolutionize our understanding of dark matter by mapping the universe's structure with unprecedented precision. Dark matter is more than just a mysterious substance. It is the foundation upon which the universe's largest structures are built. Its invisible influence has shaped the cosmos from the smallest galaxies to the largest walls and filaments. As we continue to explore its secrets, we not only uncover the story of dark matter, but also the grand narrative of the universe itself, a story written in the invisible ink of gravity and structure. When we speak of the largest structures in the universe, the cosmic web, great walls, and superclusters, it is essential to understand an inherent limitation: the observable universe. This term defines the region of space from which light has had enough time to reach us since the beginning of the cosmos. Beyond this boundary lies the whole universe, a realm that may be infinitely vast, filled with structures we may never see or measure. The observable universe has a radius of approximately 46.5 billion light-years, a staggering distance shaped by the finite speed of light and the age of the universe, which is about 13.8 billion years. At first glance, this seems contradictory. How can we observe light from distances greater than the universe's age? The answer lies in the universe's expansion. As space stretches, the distance between objects grows, meaning that light emitted billions of years ago from distant galaxies has traveled farther than it would in a static universe. Within this observable sphere, we can identify and study vast structures such as the Hercules Corona Borealis Great Wall and the Sloan Great Wall, as well as the countless galaxies, clusters, and voids that form the cosmic web. However, this observable boundary is not static. With every passing year, light from slightly more distant regions reaches us, gradually expanding our view of the cosmos. Even so, the ultimate horizon of observation is defined by the cosmic microwave background, CMB, the faint afterglow of the Big Bang, which serves as a backdrop to the observable universe. Despite its enormity, the observable universe is only a fraction of the whole universe. According to most cosmological models, the universe is either much larger than the observable region or truly infinite in size. If the latter is true, the structures we study may represent just a tiny sample of a universe teeming with countless other cosmic webs, voids, and walls stretching endlessly in all directions. The idea of an infinite universe raises profound questions about its contents and structure. Could there be structures even larger than the Hercules Corona Borealis Great Wall? If the universe is infinite, then logically, it must contain regions where matter is distributed differently from what we observe, including areas with potentially denser or more intricate arrangements. Alternatively, the whole universe could be finite but unbounded, like the surface of a sphere, curving back on itself in higher dimensions. The distinction between the observable universe and the whole universe also underscores the limitations of our current understanding. The laws of physics that govern the cosmos are based on what we can observe, but what if conditions beyond our horizon differ? Could alternate regions of the universe have different physical constants, laws, or even forms of matter? Such possibilities open the door to concepts like the multiverse, where our universe is just one of many within a larger, more complex reality. The expansion of the universe plays a crucial role in shaping our observable limits. Driven by dark energy, this expansion is accelerating, meaning that distant regions of space are moving away from us at ever-increasing speeds. Eventually, some galaxies will recede so quickly that their light will never reach us, effectively disappearing beyond the cosmic horizon. This phenomenon, known as cosmic event horizons, ensures that the observable universe is finite and ever-changing. The relationship between the observable universe and the whole universe also affects how we interpret the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. Observations of the observable universe generally support this principle, but it may not hold true for the entirety of the cosmos. For instance, if the whole universe is infinite, there could be regions with vastly different distributions of matter or unique structures that challenge our assumptions about cosmic uniformity. The observable universe also raises fascinating questions about the universe's ultimate fate. As dark energy dominates and expansion accelerates, the cosmic web will fragment, isolating galaxies and clusters from one another. In the distant future, the observable universe may shrink, containing only the remnants of our local structures, while the whole universe continues to evolve beyond our reach. Despite these limitations, the observable universe is an extraordinary laboratory for studying the cosmos. Within its boundaries, we can explore phenomena ranging from the birth of galaxies to the behavior of dark matter and the effects of dark energy. By studying the structures we can observe, we gain insights into the processes that likely govern the whole universe, even in regions we cannot see. In considering the relationship between the observable and the whole universe, we are reminded of the humility that comes with cosmic exploration. Our perspective is inherently limited by the speed of light, the age of the universe, and the vastness of space. Yet, within these constraints, we have uncovered patterns and structures of incredible complexity, each one a testament to the universe's grand design. What lies beyond the observable universe remains one of the greatest mysteries of modern science. Is it an infinite expanse of similar structures, a patchwork of wildly different regions, or something entirely beyond comprehension? These questions drive the ongoing search for deeper understanding, inspiring new theories, technologies, and observations. The observable universe serves as both a window and a mirror. It offers a glimpse into the cosmos' vast complexity while reflecting the limits of human perception and knowledge. As we continue to explore its boundaries, we move closer to answering the fundamental questions of existence. How vast is the cosmos, and what is our place within it? The universe is a dynamic entity, constantly evolving across billions of years. The largest structures in the cosmos, galaxies, clusters, superclusters, voids, and great walls, are not static. They grow, shift, and transform under the influence of cosmic forces such as gravity, dark matter, and dark energy. Understanding how these massive structures change over time is key to unraveling the story of the universe's formation, evolution, and eventual fate. The origins of cosmic structures can be traced back to the moments following the Big Bang. Initially, the universe was a nearly uniform sea of energy and matter, punctuated by tiny fluctuations in density. These fluctuations, imprinted in the cosmic microwave background, CMB, served as seeds for the structures we see today. Gravity amplified these slight irregularities, pulling matter together to form the first stars, galaxies, and clusters. As time passed, these early formations grew larger and more complex. Small galaxies merged to form larger ones, while groups of galaxies coalesced into clusters. Along the filaments of the cosmic web, matter continued to flow into dense regions, fueling the growth of superclusters and great walls. This process of hierarchical formation is a hallmark of the universe's evolution, driven by the interplay of gravity and the expanding fabric of space. One of the most striking aspects of these changes is the role of galactic mergers. When galaxies collide, their shapes and internal structures are dramatically altered. Spiral galaxies, for instance, can lose their delicate arms and transform into elliptical galaxies, which are more common in dense regions like clusters. These mergers also trigger bursts of star formation, as gas clouds collide and collapse under gravity. Over billions of years, repeated mergers have built the massive galaxies we see at the centers of clusters today. Clusters themselves evolve through a similar process. Smaller clusters and groups are drawn together by gravity, eventually merging to form larger systems. These collisions are violent events, generating shockwaves in the intracluster gas and leaving behind intricate patterns of hot and cold regions. The bullet cluster, a famous example of such a merger, reveals the separation of dark matter and ordinary matter, providing critical insights into the nature of both. Superclusters and great walls, while slower to evolve, are also shaped by the flow of matter through the cosmic web. As galaxies and clusters migrate along filaments, they accumulate in dense regions, adding to the size and complexity of these structures. However, the growth of these colossal formations is not unlimited. The universe's accelerated expansion, driven by dark energy, is gradually halting the flow of matter, effectively freezing the growth of the largest structures. Dark energy's influence on the evolution of cosmic structures is profound. As it drives the universe's expansion, dark energy counteracts the pull of gravity, preventing matter from clustering on the largest scales. This means that the era of structure formation is coming to an end. In the distant future, the cosmic web will become less dynamic, with galaxies, clusters, and superclusters effectively locked in to their current configurations. Despite this slowdown, smaller-scale interactions will continue to shape the universe for billions of years. For instance, the Milky Way and Andromeda Galaxy are on a collision course, expected to merge in about 4.5 billion years. This event will reshape both galaxies, likely forming a massive elliptical galaxy. Similar mergers are occurring throughout the universe, contributing to the ongoing evolution of galaxies and clusters. Voids, too, are evolving, albeit in a different way. These vast empty regions are growing larger as matter flows out of them and into surrounding filaments and clusters. Over time, voids will dominate the universe's structure, with dense regions becoming increasingly isolated from one another. This process highlights the dynamic balance between density and emptiness that defines the cosmic web. The future of these structures is intricately tied to the fate of the universe itself. If dark energy continues to dominate, as current observations suggest, the expansion of the universe will accelerate indefinitely. This scenario, known as the Big Freeze, will cause galaxies and clusters to drift apart, leaving behind isolated pockets of matter in an ever-expanding void. Eventually, even stars within galaxies will burn out, leaving a cold, dark cosmos. Alternatively, if dark energy's behavior changes over time, it could lead to different outcomes. A big crunch, where the universe's expansion reverses and everything collapses back together, would compress the cosmic web into a singularity, erasing all structures. Another possibility, the Big Rip, involves dark energy tearing apart galaxies, stars, and even atoms as its influence grows stronger. In addition to these cosmic scale changes, the internal dynamics of structures also evolve. Within galaxy clusters, stars continue to form, live out their life cycles, and die, contributing to the enrichment of the intracluster medium with heavier elements. Supermassive black holes at the centers of galaxies grow by accreting matter, releasing powerful jets and outflows that shape their surroundings. These processes ensure that even within seemingly stable structures, constant change is occurring. The evolution of cosmic structures also provides critical insights into the nature of dark matter and dark energy. By studying how galaxies and clusters grow and interact over time, astronomers can test theories about the composition and behavior of these mysterious forces. For instance, simulations of structure formation in the presence of dark matter closely match observed patterns in the cosmic web, providing strong evidence for its existence. Technological advances are enabling scientists to study these changes in unprecedented detail. Observatories like the James Webb Space Telescope and the Vera C. Rubin Observatory are peering deeper into the cosmos, capturing light from the universe's earliest structures. These observations, combined with powerful simulations, allow researchers to reconstruct the universe's history and predict its future. The story of the universe's largest structures is one of constant transformation, driven by the relentless forces of gravity, expansion, and time. From the tiny fluctuations of the early cosmos to the grand patterns of the cosmic web, these structures have grown and evolved, shaping the universe into the magnificent tapestry we see today. As we continue to explore their changes, we deepen our understanding of the universe's past, present, and ultimate destiny. Gravity is the cosmic sculptor, the fundamental force responsible for shaping the universe's grandest structures. From the formation of stars and galaxies to the intricate patterns of the cosmic web, gravity orchestrates the flow of matter across the cosmos, creating order out of chaos. Without gravity's relentless pull, the universe would be a vastly different place, an unstructured expanse of particles drifting aimlessly through space. The story of gravity begins in the earliest moments of the universe. Shortly after the Big Bang, the universe was a nearly uniform sea of energy and matter, with tiny fluctuations in density imprinted by quantum effects. Gravity acted on these fluctuations, amplifying them over time. Denser regions attracted more matter, becoming the seeds of galaxies, clusters, and larger structures. This process, known as gravitational collapse, is the foundation of cosmic structure formation. On smaller scales, gravity's effects are immediately visible. Stars form when clouds of gas and dust collapse under their own weight, igniting nuclear fusion in their cores. These stars group together to form galaxies, held in place by their mutual gravitational attraction. Within galaxies, gravity governs the orbits of stars around the galactic center, shaping their spiral or elliptical forms. The massive black holes at the cores of many galaxies exert extreme gravitational forces, influencing nearby stars and gas clouds. On larger scales, gravity's influence extends far beyond individual galaxies. It binds galaxies into clusters, the most massive gravitationally bound systems in the universe. These clusters, in turn, are connected by filaments of the cosmic web, vast networks of dark matter and gas that stretch across hundreds of millions of light years. Gravity pulls matter along these filaments, funneling it into dense nodes where clusters and superclusters form. The cosmic web, with its intricate patterns of filaments, nodes, and voids, is perhaps the clearest demonstration of gravity's large-scale power. Simulations of the universe's evolution show how gravity shapes this web over billions of years, drawing matter into dense regions while leaving behind vast empty voids. This dynamic interplay creates the universe's strikingly interconnected structure, with gravity acting as the invisible hand that guides its formation. The role of gravity is not limited to visible matter. Dark matter, the unseen substance that makes up most of the universe's mass, interacts with ordinary matter primarily through gravity. Dark matter forms massive halos around galaxies and clusters, providing the gravitational framework for their stability and growth. Without the extra gravitational pull of dark matter, galaxies would not rotate as quickly as they do, and clusters would not hold together. Gravitational interactions also shape the evolution of galaxies and clusters. When galaxies pass near each other, their mutual gravity creates tidal forces that distort their shapes and can strip away stars and gas. These interactions, often called tidal interactions, can trigger bursts of star formation or even lead to galaxy mergers. Over time, such mergers build larger galaxies and contribute to the growth of clusters. In galaxy clusters, gravity holds together not only the galaxies but also the hot gas that fills the spaces between them. This gas, known as the intracluster medium, is heated to extreme temperatures by gravitational forces, emitting X-rays that provide valuable insights into the cluster's mass and structure. The gravitational potential of a cluster also bends light from background objects, creating gravitational lensing effects that allow astronomers to study the distribution of dark matter. On the scale of superclusters and great walls, gravity continues to play a central role. These colossal structures form as matter flows along filaments, drawn into dense regions by gravity. Over billions of years, gravity has shaped these formations into the largest coherent structures in the observable universe, connecting clusters and superclusters into a vast cosmic network. While gravity is the primary force driving the formation of structures, its influence is increasingly counteracted by dark energy, the mysterious force responsible for the accelerated expansion of the universe. As dark energy pushes galaxies and clusters apart, it limits the growth of large-scale structures. In the distant future, gravity's role will diminish as dark energy dominates, leaving galaxies and clusters isolated in a vastly expanded universe. Despite this eventual fate, gravity's influence is not entirely one-directional. It also creates dynamic phenomena that reveal the interconnectedness of the cosmos. For example, gravitational waves, ripples in space-time caused by massive accelerating objects, propagate across the universe, carrying information about their origins. These waves, first detected in 2015, provide a new way to study cosmic events, such as black hole mergers, and highlight gravity's role in shaping extreme environments. The study of gravity has evolved dramatically since Isaac Newton first described it as a universal force of attraction. Albert Einstein's theory of general relativity transformed our understanding of gravity, revealing it as the curvature of space-time caused by mass and energy. This framework explains not only everyday gravitational effects, but also cosmic phenomena like gravitational lensing, black holes, and the dynamics of the universe as a whole. Gravity's role in the cosmos is deeply intertwined with the universe's other fundamental forces and components. For example, gravity works alongside pressure and radiation to regulate star formation and determine the structure of galaxies. It interacts with dark matter to shape the cosmic web and with dark energy to dictate the universe's large-scale evolution. This interplay highlights the complexity of the forces shaping the cosmos and the centrality of gravity in holding it all together. As we explore gravity's influence, we also confront its mysteries. Why does gravity, the weakest of the four fundamental forces, dominate the large-scale structure of the universe? How does it interact with dark matter and dark energy? And could there be undiscovered aspects of gravity that explain phenomena like the accelerated expansion of the universe? These questions drive ongoing research and inspire the search for a deeper understanding of the cosmos. Gravity is more than a force. It is the architect of the universe. From the smallest stars to the largest walls and filaments, gravity sculpts the cosmos into a vast, interconnected tapestry. Its influence spans the entire history of the universe, shaping not only what we see today, but also what will emerge in the eons to come. As we study gravity, we uncover the mechanisms that have crafted the universe's beauty and complexity, bringing us closer to understanding the grand design of the cosmos. The universe is not merely expanding, it is accelerating, driven by an enigmatic force that scientists have named dark energy. This mysterious phenomenon, which accounts for about 68% of the universe's total energy content, is reshaping the cosmos, influencing the fate of its largest structures, and challenging our understanding of the fundamental forces at work in the universe. Dark energy was first discovered in the late 1990s when astronomers studying distant supernovae noticed something unexpected. Instead of slowing down due to gravity, the expansion of the universe was speeding up. This revelation overturned decades of assumptions about the cosmos and introduced dark energy as the dominant factor in its evolution. Unlike gravity, which pulls matter together, dark energy exerts a repulsive force, causing space itself to stretch. This repulsion affects the growth of cosmic structures in profound ways. While gravity remains the primary driver of structure formation on smaller scales, dark energy increasingly dominates on larger scales, halting the growth of superclusters and great walls and isolating galaxies and clusters from one another. The effects of dark energy can be observed in the cosmic microwave background, CMB, the faint glow of radiation left over from the Big Bang. Tiny variations in the CMB provide a snapshot of the universe's early structure and offer clues about the influence of dark energy. By studying these variations, astronomers can measure the geometry of the universe, which reveals how dark energy has shaped its expansion over time. On the scale of the cosmic web, dark energy's influence is becoming more pronounced. As space expands, the flow of matter along filaments slows, reducing the rate at which galaxies and clusters merge. Over billions of years, this process will lead to a freeze in the growth of the largest structures, locking them into their current configurations. In the distant future, the once dynamic cosmic web may appear static, with galaxies and clusters trapped in isolated pockets. The accelerating expansion caused by dark energy also affects our ability to observe the universe. As galaxies recede faster, their light shifts to longer wavelengths, becoming fainter and eventually disappearing from view. This phenomenon, known as the cosmic event horizon, defines the ultimate limit of what we can observe. Beyond this horizon, galaxies are moving away so quickly that their light will never reach us, effectively cutting off our view of the broader universe. The role of dark energy is not limited to its effects on large-scale structure. It also shapes the overall geometry of the cosmos. Observations suggest that the universe is flat, meaning its expansion is finely balanced between eternal growth and eventual collapse. This flatness implies that dark energy exerts a constant pressure, maintaining the universe's delicate equilibrium. Despite these insights, the nature of dark energy remains one of the greatest mysteries in science. Several theories have been proposed to explain it, ranging from a cosmological constant, as described in Einstein's equations of general relativity, to more exotic ideas like quintessence, a dynamic field that evolves over time. Other hypotheses suggest that dark energy could be a manifestation of unknown physics, such as modifications to gravity on cosmological scales. The study of dark energy is advancing rapidly, with new observations providing critical data. Projects like the Dark Energy Survey, DES, and the Euclid Space Telescope are mapping the distribution of galaxies and cosmic structures, revealing how dark energy influences their growth. By comparing these observations with theoretical models, scientists are narrowing down the possible explanations for dark energy's nature and behavior. Dark energy's expanding role has profound implications for the fate of the universe. If dark energy remains constant, as the cosmological constant model predicts, the universe will continue to expand at an accelerating rate, leading to a scenario known as the Big Freeze. In this future, galaxies will drift apart, stars will burn out, and the universe will become a cold, dark void. Alternatively, if dark energy's properties change over time, the universe's fate could be very different. A Big Rip scenario, for instance, occurs if dark energy's repulsive force grows stronger. In this case, dark energy would eventually overpower all other forces, tearing apart galaxies, stars, planets, and even atoms. Conversely, if dark energy weakens or reverses, the universe could experience a big crunch, collapsing back into a singularity. The influence of dark energy also raises philosophical and existential questions. Why does dark energy exist? Is it a fundamental property of the universe, or does it arise from deeper, unknown physics? And how does its presence shape our understanding of the cosmos and our place within it? These questions highlight the profound implications of dark energy, not just for astronomy, but for our understanding of reality itself. Dark energy's impact on the universe is not limited to the distant future. It is already shaping the way we explore the cosmos. As telescopes and observatories probe deeper into space, they are encountering the limits imposed by dark energy's effects. These constraints challenge scientists to develop innovative techniques for observing and modeling the universe, pushing the boundaries of human knowledge. Ultimately, dark energy represents the greatest frontier in cosmology, a force that is both mysterious and transformative. Its expanding role in the universe's evolution underscores the complexity and interconnectedness of cosmic phenomena. As we study dark energy, we are not only uncovering the mechanisms that govern the universe, but also confronting the profound mysteries that define its existence. Amid the cosmic web of galaxies, clusters, and superclusters, certain galaxies stand out as true titans. These megagalaxies, the largest and most massive galaxies in the universe, are the result of billions of years of mergers, growth, and gravitational interactions. Towering over their smaller counterparts, they are often found in the densest regions of galaxy clusters and play a pivotal role in shaping their environments. A megagalaxy is defined not only by its immense size, but also by its staggering mass. Some of these colossal systems contain trillions of stars and vast amounts of dark matter, gas, and dust. The largest known galaxy, IC 1101, is a prime example. Located in the Abell 2029 galaxy cluster, IC 1101 stretches more than 5.5 million light-years in diameter, over 50 times the size of the Milky Way. Its sheer scale defies imagination, encompassing more mass than many smaller galaxy clusters. The formation of megagalaxies is a story of cosmic evolution and gravitational dominance. In the early universe, smaller galaxies were more common, but over time, they began to merge, pulled together by gravity. These mergers often occurred in dense environments like galaxy clusters, where interactions between galaxies are frequent. Over billions of years, repeated mergers created larger and larger systems, culminating in the formation of the massive elliptical galaxies that dominate the centers of clusters today. Unlike the spiral galaxies that populate less dense regions, megagalaxies are almost always elliptical in shape. Their smooth, featureless profiles are a testament to their violent origins. During mergers, the delicate structure of spiral arms is disrupted, and the resulting galaxy becomes more spherical or elongated. These galaxies also tend to have older stellar populations, as the bursts of star formation triggered by mergers gradually subside. At the heart of nearly every megagalaxy lies a supermassive black hole, often billions of times the mass of the Sun. These black holes play a central role in the evolution of their host galaxies. As they accrete matter, they release enormous amounts of energy in the form of radiation and jets, which can influence the surrounding environment. This feedback process, known as AGN, active galactic nucleus feedback, can regulate star formation by heating or expelling gas, preventing it from cooling and forming new stars. Megagalaxies also contain vast reservoirs of hot gas, which permeate their surroundings and emit X-rays. This gas is often a relic of past mergers and interactions, enriched with heavier elements produced by generations of stars. In some cases, the gas forms extended halos that can stretch far beyond the visible edges of the galaxy, blending into the intracluster medium of the surrounding cluster. Despite their massive size, megagalaxies are not static entities. They continue to grow by accreting smaller galaxies, a process known as galactic cannibalism. In dense cluster environments, smaller galaxies often spiral inward, drawn by the gravitational pull of the central megagalaxy. Over time, they are absorbed, adding to the mass and size of the larger system. This process is ongoing, as even the largest galaxies are surrounded by a swarm of smaller companions waiting to be consumed. The influence of megagalaxies extends beyond their immediate surroundings. Their immense gravitational pull affects the motion of nearby galaxies and even shapes the structure of the galaxy cluster as a whole. In some cases, the gravitational lensing effects of a megagalaxy can magnify and distort the light from background objects, providing valuable insights into the distribution of dark matter within and around the galaxy. Megagalaxies also play a role in the dynamics of the cosmic web. As the largest nodes in the network of filaments, they serve as anchor points for the flow of matter through the universe. Gas and galaxies streaming along filaments are drawn into the dense regions where megagalaxies reside, fueling their growth and contributing to the ongoing evolution of the cosmic web. Studying megagalaxies provides valuable insights into the universe's history and future. By examining their properties, astronomers can learn about the processes that drove galaxy formation and evolution over billions of years. For instance, The size and mass of a megagalaxy can reveal details about its merger history, while the composition of its stars and gas offers clues about the enrichment of the universe with heavy elements. Technological advancements have made it possible to study these colossal systems in unprecedented detail. Observatories like the James Webb Space Telescope and the Chandra X-ray Observatory are probing the innermost regions of megagalaxies, revealing the interplay between their supermassive black holes, stars, and gas. Meanwhile, large-scale surveys are mapping their distribution across the universe, providing a broader context for their role in the cosmic web. Despite their dominance, megagalaxies are not eternal. In the distant future, as the universe continues to expand, they may become increasingly isolated. The accelerated expansion driven by dark energy will push galaxies and clusters apart, leaving megagalaxies stranded in an ever-growing void. Over trillions of years, their stars will burn out, and the galaxies will fade into darkness, becoming relics of a more dynamic cosmic era. Megagalaxies are not just the giants of the universe. They are its history books, preserving the story of cosmic evolution in their immense mass and intricate structure. As we study these colossal systems, we uncover the processes that have shaped the universe on the largest scales, gaining a deeper appreciation for the complexity and grandeur of the cosmos. Between the galaxies that light up the universe lies a vast and largely invisible realm known as the intergalactic medium, IGM. This diffuse expanse of gas and plasma fills the space between galaxies, acting as the connective tissue of the cosmic web. While it may seem like a void to the naked eye, the intergalactic medium is a dynamic and essential component of the universe, shaping the growth of galaxies, clusters, and large-scale structures. The intergalactic medium primarily consists of hydrogen and helium, the two lightest and most abundant elements created during the Big Bang nucleosynthesis. However, over billions of years, it has been enriched with heavier elements such as carbon, oxygen, and nitrogen, produced by stars and distributed through supernova explosions and galactic outflows. This enrichment process links the IGM to the life cycle of stars and galaxies, highlighting its role as a reservoir for cosmic evolution. The IGM is not uniform. Instead, it follows the structure of the cosmic web, concentrated along filaments and nodes where galaxies and clusters form, while being sparse in the vast voids that separate these dense regions. Within these filaments, the IGM acts as a bridge, funneling gas into galaxies and clusters and sustaining their growth. This flow of material is driven by gravity, which pulls gas along the web's filaments into dense regions. One of the most significant phases in the history of the IGM occurred during reionization, a period that began about 400 million years after the Big Bang. Before reionization, the IGM was mostly neutral, with hydrogen atoms in a non-ionized state. As the first stars and galaxies formed, their intense radiation ionized the surrounding hydrogen, transforming the IGM into a hot, ionized plasma. This epoch marked a critical turning point in cosmic history, allowing light to travel freely through the universe and illuminating the structures we see today. Despite its importance, the IGM is challenging to observe directly because of its low density and faint emissions. However, astronomers have developed ingenious methods to study it. One of the most effective techniques involves the Lyman alpha forest, a series of absorption lines in the spectra of distant quasars. As light from a quasar travels through the IGM, it interacts with neutral hydrogen along the way, creating a pattern of absorption lines that reveals the density and distribution of the gas. These observations provide a detailed map of the IGM and its connection to the cosmic web. The intergalactic medium also plays a crucial role in galaxy formation and evolution. Galaxies grow by accreting gas from the IGM, which provides the raw material for star formation. In some cases, this gas flows smoothly into galaxies along filaments, a process known as cold mode accretion. In other instances, the gas is heated to high temperatures, requiring it to cool before condensing into stars. The balance between these modes of accretion shapes the diversity of galaxies we observe today. The IGM is not just a source of material for galaxies. It also acts as a sink, absorbing energy and elements expelled by galactic outflows. Supernovae and active galactic nuclei, AGN, drive winds that push gas, metals, and radiation into the intergalactic medium, enriching it and influencing its thermal state. This feedback loop links the IGM to the processes occurring within galaxies, creating a dynamic exchange of matter and energy. On the largest scales, the intergalactic medium affects the evolution of galaxy clusters and superclusters. The gas in the IGM can accumulate in the densest regions of the cosmic web, forming the intracluster medium, ICM, that fills galaxy clusters. This hot, X-ray emitting gas provides valuable insights into the mass and dynamics of clusters, as well as the distribution of dark matter. Recent observations have revealed that the IGM is far more complex than previously thought. For example, fast radio bursts, FRBs, short and intense pulses of radio waves, have been used to probe the IGM's density and composition. These bursts interact with the intergalactic medium as they travel, leaving behind signatures that astronomers can analyze to better understand the properties of the gas. Similarly, gravitational lensing has been used to study the distribution of matter in the IGM, offering new perspectives on its role in the cosmic web. The IGM also interacts with dark matter and dark energy, two of the most enigmatic components of the universe. Dark matter provides the gravitational scaffolding that shapes the IGM's distribution, while dark energy influences the expansion of the universe, stretching the IGM and affecting its density over time. These interactions highlight the interconnectedness of the universe's fundamental components, with the IGM serving as a bridge between visible and invisible phenomena. As the universe evolves, the intergalactic medium will continue to change. In the distant future, as dark energy drives the accelerated expansion of the cosmos, the IGM will become increasingly diffuse, with galaxies and clusters drifting further apart. The flow of gas along filaments will slow, reducing the supply of material for star formation and altering the dynamics of galaxy evolution. Eventually, the IGM may become so rarefied that it no longer plays a significant role in the universe's structure. The intergalactic medium, though invisible to the naked eye, is a cornerstone of the universe's architecture. It connects galaxies and clusters, drives their growth, and holds the key to understanding the large-scale structure of the cosmos. By studying the IGM, we uncover not only the hidden dynamics of the universe, but also the processes that have shaped it over billions of years. It is a reminder that even in the vast emptiness of space, there is a complex and vibrant story waiting to be told. In a universe teeming with galaxies, clusters, and cosmic webs, it is easy to overlook the vast stretches of emptiness that lie in between. Yet, these regions, known as voids, are just as important as their denser counterparts. Among them, the supervoids, the largest known voids in the universe, stand out as cosmic deserts of unparalleled scale, spanning hundreds of millions of light years. Despite their emptiness, these colossal structures reveal critical insights into the universe's composition, evolution, and large-scale dynamics. Supervoids are regions of the cosmos where the density of matter is significantly lower than the cosmic average. They are vast, sparsely populated expanses that contain only a handful of galaxies scattered throughout their volume. While typical voids are tens of millions of light years across, supervoids can stretch to sizes exceeding 300 million light years. Their sheer scale makes them some of the largest individual features in the universe. One of the most famous examples is the Boötes void, located about 700 million light years from Earth. Spanning approximately 330 million light years in diameter, this supervoid contains fewer than 60 galaxies, a striking contrast to the dense regions of the cosmic web. Another example is the Eridanus supervoid, which has been linked to the cold spot in the cosmic microwave background, CMB. This potential connection between a supervoid and the CMB highlights the profound influence these empty regions can exert on the universe. Supervoids are not empty in the absolute sense. They still contain dark matter, gas, and a few galaxies, but their density is so low that their gravitational influence is markedly reduced. This reduced gravity affects the motion of nearby galaxies and the distribution of matter in the surrounding regions. The formation of supervoids can be traced back to the early universe, where slight underdensities in the primordial matter distribution grew larger over time as gravity pulled material into denser regions, leaving behind vast empty spaces. Despite their low density, supervoids are critical components of the cosmic web. They help define the structure of the universe, acting as counterpoints to the dense filaments and nodes that connect galaxies and clusters. Their boundaries often feature thin walls of galaxies and gas, which mark the transition from low-density voids to higher-density regions. These boundaries provide valuable insights into the processes that shape the universe's large-scale structure. The study of supervoids has advanced significantly in recent years, thanks to improvements in observational technology and analytical techniques. One of the most effective methods for studying voids involves the use of the Lyman alpha forest, a pattern of absorption lines in the spectra of distant quasars. As light from a quasar travels through the universe, it passes through regions of varying density, including voids. By analyzing these patterns, astronomers can map the distribution of voids and supervoids with remarkable precision. Another key tool for studying supervoids is the Sachs-Wolf effect, a phenomenon observed in the CMB. As light from the CMB passes through a supervoid, the reduced gravitational potential of the void causes a shift in the energy of photons. This creates subtle temperature fluctuations in the CMB, which can be detected and analyzed. The Sachs-Wolf effect has been used to identify and study the largest supervoids, providing a window into their properties and effects on the universe. Supervoids also play a significant role in testing theories of cosmology, particularly those related to dark energy and the universe's accelerated expansion. The growth and evolution of voids are influenced by the interplay between gravity and dark energy, making them natural laboratories for studying these forces. For instance, the size and distribution of supervoids can provide clues about the nature of dark energy and its impact on the large-scale structure of the universe. One of the most intriguing aspects of supervoids is their potential connection to anomalies in the CMB. The cold spot, a region of the CMB with a lower-than-expected temperature, has been hypothesized to correspond to a large supervoid. If this connection is confirmed, it would provide a direct link between the large-scale structure of the universe and the CMB, offering new insights into the early universe and the role of voids in shaping its evolution. Supervoids also raise fascinating questions about the nature of the universe. Why do such vast, empty regions exist? What processes govern their size, shape, and distribution? And could there be even larger voids beyond the observable universe? These questions highlight the importance of supervoids as a frontier in cosmology, offering new challenges and opportunities for exploration. As the universe continues to expand, supervoids will grow even larger. The accelerated expansion driven by dark energy will stretch these regions, further reducing their density and isolating the galaxies within them. Over billions of years, supervoids may become the dominant feature of the universe, with the remaining galaxies and clusters confined to isolated pockets of matter. Despite their emptiness, supervoids are far from insignificant. They are a testament to the dynamic processes that shape the universe, revealing the balance between density and void, matter and emptiness. By studying these vast cosmic deserts, we gain a deeper understanding of the universe's structure, evolution, and the forces that govern it. Supervoids remind us that the universe is not just a collection of luminous galaxies and clusters, but also a realm of profound contrasts. Their existence challenges our perceptions of emptiness and invites us to explore the hidden dynamics of the cosmos. In their silence and vastness, supervoids hold the key to some of the universe's most profound mysteries. The observable universe is the cosmic stage upon which all our understanding of the cosmos plays out. It represents the sphere of space within which light has had time to reach us since the beginning of the universe, spanning an astonishing 93 billion light-years in diameter. This immense expanse contains everything we can measure, study, and theorize about, from the smallest particles to the largest structures like galaxy superclusters and great walls. Yet, the observable universe is but a fraction of the whole, and its boundaries are defined by the interplay of light, time, and the universe's expansion. To grasp the concept of the observable universe, one must first consider the speed of light, the ultimate cosmic speed limit. Light travels at approximately 300,000 kilometers per second, 186,000 miles per second. But even at this speed, it takes billions of years to traverse the vast distances of the cosmos. Since the universe is approximately 13.8 billion years old, light from the farthest regions has had a finite amount of time to reach us, defining the observable edge of the universe. However, the observable universe extends far beyond 13.8 billion light-years due to the expansion of space. As the universe stretches, the distances between objects grow, meaning that the light we see today from the most distant galaxies was emitted billions of years ago when those galaxies were much closer. Today, those galaxies are located at distances of up to 46.5 billion light-years from Earth, defining the radius of the observable universe. Within this immense sphere lies everything we have ever observed, hundreds of billions of galaxies, each containing hundreds of billions of stars, along with countless planets, black holes, nebulae, and other phenomena. The observable universe also encompasses the cosmic microwave background, CMB, the faint afterglow of the Big Bang, which serves as the surface of the observable universe. This relic radiation provides a snapshot of the universe as it was just 380,000 years after the Big Bang, offering invaluable insights into its origins and evolution. The observable universe is not a static boundary. It grows as time passes. With each passing year, light from slightly more distant regions reaches us, expanding our view of the cosmos. However, this growth is not infinite. The accelerated expansion of the universe, driven by dark energy, creates a cosmic event horizon, beyond which galaxies recede faster than the speed of light relative to us. Light emitted from those galaxies today will never reach us, effectively placing them beyond our observational reach. Despite its immense size, the observable universe is only a fraction of the entire universe. According to most cosmological models, the universe extends far beyond what we can observe, potentially being infinite in extent. If this is true, the structures and phenomena we see in the observable universe may represent just a small sample of the cosmos as a whole. Beyond the observable horizon could lie more galaxies, superclusters, and voids, or regions of the universe that are vastly different from what we know. The observable universe is also a profound reminder of the limits of human perception. Even with the most powerful telescopes, we can only see objects that emit or reflect light. Many phenomena, such as dark matter and dark energy, are invisible to traditional observation, detectable only through their effects on visible matter. Similarly, the CMB marks the furthest point we can directly observe, as the universe was opaque to light before this epoch. The size and structure of the observable universe are deeply connected to the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. Observations of the CMB and the distribution of galaxies support this principle, revealing a universe that appears remarkably uniform when viewed from a cosmic perspective. However, structures like the Hercules Corona Borealis Great Wall challenge this notion, raising questions about whether the universe's largest scales are truly homogeneous. The observable universe is a dynamic entity, constantly evolving as the universe expands and structures grow. Galaxies form, collide, and merge, while stars are born, burn brightly, and fade away. On the largest scales, the cosmic web continues to shift and rearrange as matter flows along filaments into clusters and voids expand. Yet this dynamism is finite. As dark energy accelerates the universe's expansion, the growth of large-scale structures will slow, eventually freezing them in place. The study of the observable universe has been revolutionized by advances in technology and methodology. Ground-based observatories like the Vera C. Rubin Observatory and space-based instruments like the James Webb Space Telescope are probing deeper into space than ever before, capturing light from the universe's earliest galaxies. At the same time, simulations and theoretical models allow scientists to reconstruct the universe's history and predict its future. Philosophically, the observable universe raises profound questions about our place in the cosmos. How significant is humanity in a universe so vast? What lies beyond the observable horizon? And how do the structures within this finite sphere reflect the processes and laws that govern the universe as a whole? These questions inspire both awe and curiosity, driving the exploration of the cosmos and the search for deeper understanding. The observable universe is not just a horizon of immensity, it is a gateway to discovery. It defines the limits of what we can see and measure, yet it also points to the possibilities that lie beyond. As we continue to study its contents and boundaries, we uncover the story of the cosmos itself, a narrative written in light, gravity, and the relentless expansion of space. The universe is filled with ripples in space-time, known as gravitational waves, faint tremors that propagate through the cosmos at the speed of light. These waves, first predicted by Albert Einstein in his theory of general relativity, are caused by the most violent and energetic events in the universe. Collisions of black holes, mergers of neutron stars, and even the universe's earliest moments. Though invisible to the naked eye, gravitational waves carry vital information about the universe's most extreme phenomena, offering a new way to study the cosmos. Gravitational waves are disturbances in space-time itself, created when massive objects accelerate. Imagine a stone thrown into a calm pond, producing ripples that spread outward. Gravitational waves behave similarly, but they ripple through the fabric of space and time rather than water. These waves are produced whenever mass is moved or distorted, but only the most cataclysmic events generate waves strong enough to be detected. The first direct detection of gravitational waves occurred in 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, recorded ripples from the merger of two black holes 1.3 billion light-years away. This groundbreaking observation confirmed Einstein's century-old prediction and opened a new era in astronomy. Since then, dozens of gravitational wave events have been detected, revealing a hidden side of the universe that cannot be observed with light alone. Gravitational waves are unique in their ability to carry information about objects and events that are otherwise inaccessible. For example, when two black holes merge, they release energy in the form of gravitational waves equivalent to several solar masses being converted directly into space-time ripples. These waves encode details about the masses, spins, and orbital dynamics of the black holes, allowing scientists to reconstruct the event with remarkable precision. Beyond black holes, gravitational waves also reveal the secrets of neutron stars, the dense remnants of massive stars that have undergone supernova explosions. When two neutron stars collide, they produce gravitational waves accompanied by electromagnetic signals such as gamma rays, X-rays, and visible light. These multi-messenger events, like the one detected in 2017 known as GW170817, provide a wealth of information about stellar evolution, nuclear physics, and even the production of heavy elements like gold and platinum. Gravitational waves are not confined to individual events. They also provide insights into the universe's large-scale structure and evolution. For instance, as supermassive black holes merge in the centers of galaxies, they generate gravitational waves with frequencies too low to be detected by current instruments like LIGO. However, future observatories, such as the Laser Interferometer Space Antenna (LISA), will be able to detect these low-frequency waves, shedding light on the growth of black holes and the dynamics of galaxy mergers over cosmic time. The potential of gravitational waves extends even further back in time, to the earliest moments of the universe. Certain cosmological models suggest that primordial gravitational waves were generated during the epoch of cosmic inflation, a period of rapid expansion that occurred just fractions of a second after the Big Bang. These waves would carry imprints of the universe's birth, providing a direct window into the physics of the Big Bang itself. Though these primordial waves have not yet been detected, their discovery would revolutionize our understanding of the universe's origins. Gravitational waves also interact with the universe's largest structures, such as the cosmic web and galaxy clusters. As these waves travel through space, they can be influenced by the distribution of matter, offering a new way to map the universe's dark matter and test theories of gravity. In some scenarios, the observation of gravitational waves could even reveal deviations from general relativity, hinting at new physics beyond Einstein's theory. Detecting gravitational waves is a remarkable technological achievement. Instruments like LIGO and Virgo rely on interferometry, a technique that measures tiny changes in the distance between mirrors caused by passing waves. These changes are incredibly small, on the order of a fraction of the diameter of a proton. Yet the precision of these observatories allows them to detect waves from billions of light-years away. Future detectors, both on Earth and in space, will expand the range and sensitivity of gravitational wave astronomy, enabling discoveries across a wider spectrum of events and scales. Gravitational wave astronomy is a field in its infancy, yet it has already transformed our understanding of the universe. By revealing the dynamics of black holes, neutron stars, and cosmic evolution, it complements traditional observations of light, providing a more complete picture of the cosmos. This dual approach, often called multi-messenger astronomy, allows scientists to study phenomena from multiple perspectives, combining information from gravitational waves, electromagnetic radiation, and particles like neutrinos. The study of gravitational waves also inspires profound philosophical questions. What do these ripples tell us about the nature of space and time? How do they connect us to the most distant and extreme corners of the universe? And what secrets might they hold about the unseen forces that shape the cosmos? These questions highlight the transformative potential of gravitational waves as a tool for exploration and discovery. As we continue to study these ripples in space-time, we uncover a universe that is dynamic, interconnected, and far more complex than we ever imagined. Gravitational waves remind us that the cosmos is not static, but alive with motion, energy, and interaction. They are the echoes of creation, carrying the stories of the universe's most dramatic moments across billions of years and light years. With each new detection, we move closer to understanding the grand narrative of the cosmos, written in the subtle but powerful language of space-time. In the grand tapestry of the universe, galaxies are not static islands but dynamic systems that interact, collide, and merge over cosmic timescales. These galactic mergers are some of the most transformative events in the life of a galaxy, reshaping their structure, triggering bursts of star formation, and influencing the growth of their central black holes. The legacy of these mergers is written in the stars, gas, and dark matter of galaxies, offering clues about the processes that have shaped the universe. Galactic mergers occur when two or more galaxies are drawn together by their mutual gravitational attraction. These events are most common in dense regions of the universe, such as galaxy clusters, where interactions are frequent. However, even in less crowded environments, the long-range pull of gravity ensures that galaxies in proximity will eventually collide. The outcome of these encounters depends on the size, speed, and angle of the galaxies involved, creating a diverse array of merger scenarios. The most dramatic mergers involve two galaxies of similar size, a process known as a major merger. These collisions are often chaotic, as the gravitational forces between the galaxies distort their shapes, creating tidal tails, bridges of stars and gas, and other intricate structures. Over millions of years, the galaxies lose their distinct identities, merging into a single, larger galaxy. Major mergers typically result in the formation of elliptical galaxies, which are smooth and featureless compared to the spiral shapes of their progenitors. In contrast, minor mergers occur when a large galaxy absorbs a much smaller one, often referred to as galactic cannibalism. In these cases, the larger galaxy retains its overall structure while incorporating the stars, gas, and dark matter of the smaller galaxy. The Milky Way, for instance, has undergone numerous minor mergers throughout its history, and evidence of these events can be seen in the streams of stars left behind by disrupted dwarf galaxies. One of the most iconic examples of a galactic merger is the ongoing collision between the Antennae galaxies, located about 45 million light-years away. These two spiral galaxies are in the process of merging, creating spectacular tidal tails and regions of intense star formation. Similarly, the Milky Way and the Andromeda Galaxy are on a collision course, expected to merge in about 4.5 billion years. This event will transform both galaxies, likely creating a massive elliptical galaxy dubbed Milkomeda. Star formation is one of the most striking consequences of galactic mergers. As galaxies collide, their gas clouds are compressed, triggering the formation of new stars at rates far higher than normal. These bursts of star formation, known as starbursts, can light up the merging galaxies, making them some of the brightest objects in the universe. Over time, however, the gas reservoirs are depleted, leading to a decline in star formation and the eventual quenching of the galaxy. Mergers also have a profound impact on the supermassive black holes at the centers of galaxies. As the galaxies merge, their central black holes are drawn together, eventually forming a binary system. These black holes interact with their surroundings, accreting gas and releasing energy in the form of jets and radiation. The final stages of the merger produce gravitational waves, ripples in space-time that can be detected by observatories like LIGO and the upcoming Laser Interferometer Space Antenna, LISA. The legacy of galactic mergers extends beyond individual galaxies. On larger scales, mergers drive the growth of galaxy clusters, the most massive gravitationally bound structures in the universe. Within clusters, galaxies frequently interact, exchanging material and altering their shapes. These interactions contribute to the hierarchical growth of the cosmic web, where small structures merge to form larger ones over billions of years. The effects of galactic mergers can also be seen in the distribution of stars and gas. For example, the stellar halos of many galaxies contain stars that were stripped from smaller galaxies during mergers. Similarly, streams of gas left behind by disrupted galaxies can create bridges between galaxies or enrich the intergalactic medium with heavy elements. These remnants serve as a record of the galaxy's history, providing a window into past interactions and collisions. Galactic mergers are not always destructive. They also foster creativity and transformation. The mixing of stars and gas from different galaxies can create unique structures, such as ring galaxies, where stars and gas are arranged in a circular pattern. These structures are rare and often short-lived, but highlight the diverse outcomes of galactic interactions. The study of galactic mergers has advanced significantly with the help of simulations and observations. High-resolution simulations, such as those from the Illustris and Eagle projects, model the physics of galaxy formation and merging, revealing how these events unfold over time. Observatories like the Hubble Space Telescope and the James Webb Space Telescope have captured stunning images of merging galaxies, providing direct evidence of these dynamic processes. Galactic mergers are also critical for understanding the role of dark matter in galaxy formation. The dark matter halos surrounding galaxies influence the dynamics of mergers, shaping how galaxies interact and merge. Observing the effects of dark matter during mergers offers valuable insights into its properties and distribution. In the distant future, as dark energy continues to drive the expansion of the universe, galactic mergers will become less common. Galaxies that are gravitationally bound, such as those in the local group, will merge to form larger systems, while more distant galaxies drift beyond the cosmic horizon. This process will eventually leave behind isolated island galaxies, remnants of a more interconnected cosmic era. Galactic mergers are a testament to the dynamic and ever-changing nature of the universe. They are both destructive and creative, tearing apart galaxies while forging new ones. As we study these cosmic collisions, we uncover the forces that shape the cosmos and the intricate dance of gravity, matter, and energy that defines the universe's evolution. Beyond the bright disks of galaxies, where stars cluster in spirals or ellipticals, lies a vast and diffuse region known as the galactic halo. This halo extends far beyond the visible edges of galaxies, encompassing old stars, globular clusters, and, crucially, star streams, long, tenuous trails of stars stretching across the halo. These streams, remnants of ancient interactions and mergers, are not just beautiful. They are cosmic time capsules, preserving the history of galaxy formation and evolution. Star streams form when smaller galaxies or star clusters venture too close to a larger galaxy and are torn apart by its gravitational forces. As the smaller system is disrupted, its stars are scattered, forming elongated trails that trace the orbit of the original structure. These streams can span tens to hundreds of thousands of light years, winding their way through the galactic halo in intricate patterns. One of the most famous examples of a star stream is the Sagittarius Stream, a sprawling structure that wraps around the Milky Way. This stream is the remnant of the Sagittarius dwarf elliptical galaxy, which is currently merging with the Milky Way. As the dwarf galaxy is gradually disrupted, its stars are stripped away, creating a looping stream that provides a direct view of an ongoing galactic merger. Star streams are more than just remnants of smaller galaxies. They are also a critical tool for studying the structure and dynamics of their host galaxies. By mapping the positions and motions of stars within these streams, astronomers can reconstruct the orbits of the disrupted systems, revealing the gravitational potential of the host galaxy. This, in turn, provides insights into the distribution of dark matter, which dominates the mass of the galactic halo and shapes the orbits of stars. The study of star streams has been revolutionized by modern telescopes and surveys. Projects like the Sloan Digital Sky Survey, SDSS, and the European Space Agency's Gaia mission have mapped the positions, velocities, and chemical compositions of millions of stars, allowing astronomers to identify and study star streams in unprecedented detail. Gaia, in particular, has provided three-dimensional maps of the Milky Way, revealing dozens of previously unknown streams and offering a new perspective on the galaxy's halo. Star streams also serve as a record of the Milky Way's merger history. Over billions of years, the Milky Way has grown by accreting smaller galaxies and star clusters, a process known as hierarchical assembly. Each merger leaves behind traces in the form of streams, tidal tails, and other structures. By studying these features, astronomers can piece together the Milky Way's past, identifying the galaxies it has consumed and the timescales over which these events occurred. The chemical composition of stars in a stream provides further clues about its origin. For example, stars formed in dwarf galaxies often have lower metallicities, fewer heavy elements, than those formed in larger galaxies like the Milky Way. This distinction allows astronomers to differentiate between streams formed from dwarf galaxies and those formed from globular clusters, which are dense, spherical collections of stars orbiting the galactic halo. Beyond their role in studying galaxy formation, star streams offer a unique perspective on the nature of dark matter. The paths of these streams are shaped by the gravitational field of the galaxy, which is dominated by its dark matter halo. By analyzing the orbits and disruptions of streams, scientists can infer the shape and distribution of dark matter. Some streams even hint at the presence of dark matter subhalos, small clumps of dark matter that are predicted by simulations but remain difficult to detect directly. Star streams are not confined to the Milky Way. Observations of other galaxies, such as Andromeda, have revealed similar streams winding through their halos. These streams provide a comparative view, showing that hierarchical assembly and tidal disruption are universal processes in galaxy evolution. By studying streams in multiple galaxies, astronomers can test theories of structure formation and better understand the role of environment in shaping galaxies. One of the most intriguing aspects of star streams is their potential to uncover hidden structures in the universe. For example, irregularities or gaps in a stream can indicate the presence of an unseen object, such as a dark matter subhalo or a passing dwarf galaxy. These features act as indirect evidence of phenomena that would otherwise remain invisible, making star streams a powerful tool for probing the universe's unseen components. As the universe evolves, star streams themselves change over time. The stars in a stream gradually disperse, spreading out and blending into the halo. Over billions of years, the distinct features of a stream may fade, leaving behind only subtle traces of the original structure. This process underscores the dynamic nature of galactic halos, where the remnants of past interactions are constantly reshaped by gravity and motion. Despite their transience, star streams are a reminder of the interconnectedness of galaxies. They reveal the long history of mergers and interactions that have shaped the Milky Way and other galaxies, highlighting the role of smaller systems in building larger structures. They also illustrate the delicate balance of forces, gravity, motion, and time that governs the evolution of the cosmos. As astronomers continue to map the heavens, new star streams are being discovered, each one adding a chapter to the story of galaxy formation. These streams, stretching across the dark expanse of the halo, are not just relics of the past. They are bridges to understanding the complex and dynamic processes that have shaped the universe. Through their intricate patterns, They remind us that even in the quiet outskirts of galaxies, the echoes of cosmic history are written in the stars. The universe as we see it today is a masterpiece of cosmic evolution, but its earliest chapters tell the story of how the first giants, the primordial structures, emerged from chaos. These immense formations, including the first stars, galaxies, and clusters, were born during the universe's formative years, setting the stage for the intricate cosmic web we observe today. Understanding these primordial structures unlocks the secrets of the universe's infancy and reveals how it evolved into the complex expanse of matter, energy, and light we now inhabit. Shortly after the Big Bang, about 13.8 billion years ago, the universe was a hot, dense soup of particles and radiation. During this epoch, known as the primordial plasma, tiny quantum fluctuations in density were imprinted on the fabric of space-time. These fluctuations, magnified by the process of cosmic inflation, became the seeds of structure, regions of slightly higher density that would grow under the influence of gravity. As the universe expanded and cooled, it transitioned into a state called recombination around 380,000 years after the Big Bang. During this phase, electrons and protons combined to form neutral hydrogen, making the universe transparent to light. This era gave rise to the cosmic microwave background, CMB, a faint glow that still permeates the universe and serves as a snapshot of its early state. Embedded within the CMB are patterns of density fluctuations, the precursors to the first structures. The next major milestone occurred during the Dark Ages, a period lasting hundreds of millions of years during which the universe was filled with neutral hydrogen but devoid of visible light. During this time, gravity began to amplify the density fluctuations, causing matter to clump together. These clumps eventually became the sites of the first stars and galaxies, marking the dawn of cosmic illumination. The birth of the first stars, known as Population 3 stars, was a transformative event in cosmic history. These stars were composed almost entirely of hydrogen and helium, the elements forged in the Big Bang, and lacked the heavier elements found in later generations of stars. Population 3 stars were massive and short-lived, burning through their fuel quickly and ending their lives in violent supernovae. These explosions enriched the surrounding gas with heavier elements, laying the foundation for the next generation of stars and galaxies. The first galaxies formed as gas collected within the gravitational wells created by dark matter halos. These early galaxies were much smaller and less structured than those we see today, but they were the building blocks of larger systems. As galaxies merged and grew, they began to form the first clusters and proto-superclusters, creating the scaffolding of the cosmic web. During this era, known as cosmic reionization, the light from the first stars and galaxies began to ionize the neutral hydrogen in the intergalactic medium, transforming it into a hot, ionized plasma. This process, which occurred between 500 million and 1 billion years after the Big Bang, was critical for shaping the universe's large-scale structure. Reionization cleared the way for light to travel freely through space, allowing the universe to become fully transparent. Primordial structures also include the first quasars, luminous objects powered by supermassive black holes at the centers of early galaxies. These quasars, some of which have been observed at redshifts corresponding to less than 1 billion years after the Big Bang, provide insights into the rapid growth of black holes and their role in shaping galaxies. The intense radiation from quasars influenced their surroundings, heating the intergalactic medium and driving feedback processes that regulated star formation. The formation of the first structures was driven not only by ordinary matter, but also by dark matter, which provided the gravitational framework for their growth. Dark matter halos formed the seeds of galaxies and clusters, attracting gas and guiding the assembly of larger structures. Simulations of the universe's evolution, such as the Millennium Simulation, reveal how dark matter shaped the cosmic web, creating the interconnected filaments, nodes, and voids that define the universe today. Primordial structures are not just relics of the past. They continue to influence the universe's evolution. The earliest galaxies served as the building blocks of today's massive systems, while the heavy elements forged in the first stars are present in every planet, star, and living being. Even the patterns of the cosmic microwave background provide clues about the universe's early physics, including the processes that govern inflation and the nature of dark matter and dark energy. Observing these ancient structures is one of the greatest challenges in modern astronomy. The light from the first stars and galaxies is faint and redshifted due to the expansion of the universe, making it difficult to detect. However, telescopes like the James Webb Space Telescope, JWST, are designed to peer into this distant epoch, capturing the faint infrared light from the universe's earliest objects. These observations are revolutionizing our understanding of how the first structures formed and evolved. The study of primordial structures also raises profound questions about the nature of the universe. How did the first stars ignite in a universe with no heavy elements? What role did dark matter play in shaping the earliest galaxies? And how did the transition from the Dark Ages to the Age of Light influence the universe's overall structure? These questions drive the search for new observations and theories, pushing the boundaries of human knowledge. Primordial structures are the foundation upon which the universe was built. They represent the transition from chaos to order, from a featureless expanse to the intricate patterns of galaxies, clusters, and filaments. By studying these ancient formations, we uncover the story of the universe's beginnings and gain a deeper appreciation for the processes that have shaped its evolution. The universe's first giants are not just distant objects. They are cosmic time capsules, preserving the memory of creation. In their light and structure, we find the origins of the cosmos and the seeds of everything that exists today, from the largest galaxies to the smallest atoms. Through their story, we glimpse the profound interconnectedness of the universe, a testament to the power of gravity, light, and time to create something extraordinary out of the void. The universe as we see it today, with its vast networks of galaxies, clusters, and voids, owes its existence to a remarkable event that occurred in its earliest moments: cosmic inflation. This brief but extraordinary phase of exponential expansion shaped the universe's large-scale structures, setting the stage for the intricate cosmic web we observe today. Understanding inflation not only illuminates the origins of these structures, but also reveals the fundamental physics that govern the universe. Cosmic inflation occurred within a fraction of a second after the Big Bang, between approximately 10⁻36 10⁻36 10⁻36 and 10⁻32 10⁻32 10⁻32 seconds. During this period, the universe expanded exponentially, doubling in size many times over in an unimaginably short span of time. This rapid expansion smoothed out irregularities in the universe while amplifying tiny quantum fluctuations, creating the seeds of the large-scale structures we see today. One of the key achievements of the theory of inflation is its ability to explain the homogeneity and isotropy of the universe. Observations of the cosmic microwave background, CMB, reveal that the universe is remarkably uniform in all directions, with only small variations in temperature. Inflation explains this uniformity by stretching the universe to such an extent that any initial irregularities were smoothed out, leaving behind a nearly homogeneous expanse. At the same time, inflation amplified tiny quantum fluctuations, random variations in energy at the smallest scales, into macroscopic density perturbations. These perturbations became the seeds of structure, regions of slightly higher or lower density that would later grow under the influence of gravity. The patterns of these fluctuations are imprinted in the CMB, providing a snapshot of the universe as it was just 380,000 years after the Big Bang. The growth of these initial fluctuations is governed by gravitational instability, the process by which denser regions attract more matter, becoming even denser over time. As the universe expanded and cooled, these regions grew into the filaments, nodes, and voids that define the cosmic web. Over billions of years, the interplay between gravity, dark matter, and ordinary matter transformed the tiny perturbations seeded by inflation into the vast structures we observe today. One of the most striking features of inflation is its ability to predict the scale and variance of the universe's large-scale structure. This means that the patterns of density fluctuations are statistically similar across a wide range of scales. Observations of galaxy distributions and the CMB confirm this prediction, showing that inflation accurately describes the initial conditions for the universe's evolution. Inflation also provides a framework for understanding the formation of the largest structures in the universe, such as superclusters and great walls. These colossal formations are thought to have originated from the largest density perturbations amplified during inflation. The alignment and connectivity of these structures reflect the underlying physics of inflation, as well as the influence of dark matter and dark energy on their growth. The study of inflation has been advanced by observations of the CMB, particularly those conducted by missions like the Planck satellite and the Wilkinson Microwave Anisotropy Probe, WMAP. These missions have mapped the temperature and polarization of the CMB with incredible precision, revealing patterns that provide direct evidence for inflation. For example, the primordial power spectrum, a plot of the strength of density fluctuations across different scales, matches the predictions of inflationary theory almost perfectly. Despite its successes, inflation also raises profound questions. What drove this phase of rapid expansion? The leading theory suggests that inflation was powered by a field called the inflaton, a hypothetical quantum field with a potential energy that dominated the universe during this epoch. As the inflaton field decayed, it released energy that reheated the universe, transitioning it into the hot, dense state we associate with the Big Bang. However, the exact nature of the inflaton field remains unknown, making it a central focus of ongoing research. Inflation also has implications for the ultimate fate of the universe. Some models predict that inflation could continue indefinitely in certain regions of the cosmos, creating a multiverse, a collection of universes with different properties and physical laws. In this scenario, our observable universe would be just one of countless bubbles within a larger, inflating space-time. While speculative, this idea has profound implications for our understanding of reality and the limits of scientific inquiry. Inflation's influence extends beyond the structures we can see. It also shaped the distribution of primordial gravitational waves, ripples in space-time generated during inflation. These waves would leave a distinctive imprint on the polarization of the CMB, known as B-modes. Detecting these B-modes would provide direct evidence for inflation and offer a glimpse into the physics of the early universe at energy scales far beyond what can be achieved in particle accelerators. The legacy of inflation is written in the universe's largest structures and smallest fluctuations. By studying these features, scientists gain insights into the processes that govern the universe's birth and set the stage for its evolution. Simulations of cosmic structure formation, such as the Millennium Simulation, begin with the density fluctuations predicted by inflation and accurately reproduce the observed distribution of galaxies, providing further validation of the theory. Inflation is not just a theory of the universe's beginning. It is a bridge between the quantum and the cosmic, connecting the smallest scales of physics to the largest scales of astronomy. Its predictions have been confirmed by multiple lines of evidence, yet it also opens the door to new mysteries, challenging us to explore the unknown. The story of inflation is a testament to the power of science to uncover the universe's most profound secrets. It reveals a cosmos that is not only vast and intricate, but also deeply connected, with its largest structures emerging from the tiniest fluctuations. As we continue to study inflation, we move closer to understanding the forces that shape the universe and our place within its grand design. The universe is not random. Its largest structures reveal a striking order and coherence that extend across billions of light years. Among these patterns is the filamentary alignment of galaxies within the cosmic web. This phenomenon, where galaxies' shapes and motions align with the vast filaments that connect clusters and superclusters, offers profound insights into the dynamics of structure formation and the role of dark matter in shaping the cosmos. The cosmic web, composed of filaments, nodes, and voids, is the universe's grand scaffolding, built over billions of years as matter coalesced under the influence of gravity. These filaments are the highways of the cosmos, channeling gas, galaxies, and dark matter into dense regions where clusters and superclusters form. Within these filaments, galaxies are not randomly oriented. Their shapes, spins, and motions often align with the filament's axis, revealing a subtle but pervasive order. Galaxy filamentary alignment is a direct consequence of the processes that govern structure formation. In the early universe, slight variations in density grew into the large-scale structures we observe today. As matter flowed along the filaments, the gravitational interactions between galaxies and the underlying dark matter halo influenced their alignment. Over time, this alignment became imprinted in the orientation of galaxies, creating patterns that persist across cosmic scales. The alignment is most apparent in the spin axes of spiral galaxies. Studies show that spiral galaxies within filaments tend to rotate with their spin axes aligned parallel to the filament's axis. This orientation reflects the dynamics of gas accretion and angular momentum transfer during galaxy formation. As gas flows along the filament, it imparts angular momentum to the forming galaxy, aligning its spin with the filament's direction. Elliptical galaxies, on the other hand, exhibit a different type of alignment. These galaxies, often found in the dense cores of clusters, tend to have their major axes oriented perpendicular to the filament. This alignment is thought to result from the complex interactions and mergers that shape elliptical galaxies, as well as the influence of the gravitational potential of the cluster environment. The study of galaxy filamentary alignment has been greatly advanced by large-scale surveys such as the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES. These surveys have mapped the positions, shapes, and motions of millions of galaxies, revealing the intricate connections between galaxies and their host filaments. By analyzing these data, astronomers have uncovered statistical correlations that confirm and quantify the alignment phenomenon. Filamentary alignment is not limited to individual galaxies. It also extends to galaxy clusters and superclusters. Clusters within filaments often exhibit an elongation along the filament's axis, reflecting the anisotropic gravitational collapse that formed them. Similarly, the distribution of galaxies within clusters shows alignment patterns that provide clues about the cluster's formation history and its interaction with the surrounding cosmic web. The alignment of galaxies and filaments is not just a curiosity. It is a powerful tool for studying the properties of dark matter. Filaments are composed primarily of dark matter, which provides the gravitational framework for the cosmic web. The alignment of galaxies within these filaments reflects the influence of dark matter on galaxy formation and evolution. By studying this alignment, scientists can infer the distribution and properties of dark matter on large scales. Filamentary alignment also provides insights into the role of cosmic flows, the large-scale motions of galaxies driven by the gravitational pull of the cosmic web. These flows channel matter into filaments and nodes, shaping the distribution and orientation of galaxies. By mapping these flows, astronomers can better understand the dynamics of structure formation and the interplay between gravity, dark matter, and baryonic matter. One of the most intriguing aspects of galaxy filamentary alignment is its connection to the early universe. The patterns of alignment we observe today are rooted in the density fluctuations seeded during cosmic inflation. These initial conditions set the stage for the formation of filaments and the alignment of galaxies within them. By studying alignment patterns, scientists can probe the universe's initial conditions and test models of inflation and structure formation. The alignment of galaxies also raises fascinating questions about the interconnectedness of the cosmos. Why do such patterns persist across vast scales? What role does dark energy play in shaping these alignments? And could the alignment of galaxies reveal deeper, underlying principles that govern the universe's structure? These questions highlight the importance of filamentary alignment as a frontier in cosmology. As we continue to study galaxy filamentary alignment, new technologies and methods are opening up exciting possibilities. Observatories like the Vera C. Rubin Observatory and the Euclid Space Telescope are providing deeper and more detailed maps of the cosmic web, allowing astronomers to refine their understanding of alignment patterns. At the same time, simulations of structure formation, such as the illustrious TNG project, are offering theoretical frameworks for interpreting these observations. Galaxy filamentary alignment is more than a phenomenon. It is a cosmic signature of the processes that shape the universe. It reveals the subtle interplay between gravity, dark matter, and the dynamics of galaxy formation, providing a window into the forces that govern the cosmos. As we study these patterns, we not only uncover the story of the universe's evolution, but also gain a deeper appreciation for the order and harmony that pervade its largest structures. The alignment of galaxies within filaments is a reminder that the universe is not random, but deeply connected. From the spin of a single galaxy to the structure of the cosmic web, these alignments reflect the profound influence of gravity and time, shaping the cosmos into a masterpiece of coherence and beauty. The universe, vast and complex as it is, may not be alone. The concept of the multiverse suggests that our observable universe is just one of many, existing within a larger and potentially infinite ensemble of universes. These other universes could have different physical laws, dimensions, and structures, and they may contain cosmic phenomena that dwarf even the largest structures in our own universe. Exploring multiverse theories and their implications for cosmic structures opens a door to one of the most profound questions in cosmology. Is the universe we see all that exists? The idea of the multiverse arises from several lines of theoretical and observational inquiry, with roots in quantum mechanics, cosmic inflation, and string theory. Each of these perspectives provides a different pathway to the multiverse concept, but they all converge on a central idea. The observable universe is just one region of a much larger reality. One of the most prominent multiverse scenarios emerges from eternal inflation, a variation of the cosmic inflation theory. Inflation describes a rapid expansion of the universe in its earliest moments, but in the eternal inflation model, this process never completely ends. Instead, it continues in certain regions of spacetime, creating pocket universes or bubble universes, each with its own physical properties. Our observable universe would be just one of these pockets, where inflation has ceased and the familiar processes of cosmic evolution have taken over. In the eternal inflation framework, different bubble universes could have vastly different physical constants, particle compositions, or even numbers of spatial dimensions. These differences would profoundly impact the structures within each universe. For instance, a universe with stronger gravitational forces might produce denser clusters and more compact stars, while one with weaker gravity might lack large-scale structure entirely. This diversity suggests that the cosmic web, galaxy clusters, and voids we observe may be unique to our universe. Another avenue to the multiverse arises from quantum mechanics and the many-worlds interpretation. This interpretation posits that every quantum event leads to a branching of realities, creating a multitude of parallel universes where every possible outcome occurs. While these universes might not interact with ours in a traditional sense, their existence raises questions about how structure formation might differ under slightly altered initial conditions or physical laws. String theory, a theoretical framework that attempts to unify the fundamental forces of nature, also points toward a multiverse. In string theory, the universe is composed of tiny, vibrating strings that exist in a higher dimensional space. This framework predicts the existence of a vast landscape of possible universes, each corresponding to a different configuration of these strings. The diversity of these configurations could lead to universes with drastically different geometries, cosmologies, and structures. If the multiverse exists, it may help explain certain puzzling features of our own universe, such as the fine-tuning problem. This problem arises from the observation that many physical constants, like the strength of gravity or the cosmological constant, appear finely tuned to allow the existence of complex structures like stars, galaxies, and life. In a multiverse, this fine-tuning could be explained by a kind of cosmic selection. Among the countless universes, only those with the right conditions for structure formation would give rise to observers like us. The multiverse concept also has implications for the largest structures in our own universe. If our observable universe is just one bubble within a larger multiverse, it may be influenced by interactions with other bubbles. For example, collisions between bubble universes during inflation could leave imprints on the cosmic microwave background, CMB, creating anomalies or patterns that deviate from the standard model of cosmology. Detecting such signatures would provide direct evidence for the multiverse. The idea of a multiverse also raises profound philosophical questions. If countless universes exist, what does that mean for our understanding of reality? Are we an insignificant part of an infinite ensemble, or is our universe unique in ways we cannot yet comprehend? These questions challenge traditional notions of existence and inspire new ways of thinking about the cosmos and our place within it. Observationally, testing multiverse theories is challenging, as most other universes would lie beyond the reach of our instruments. However, certain indirect clues may offer glimpses of a multiverse. Anomalies in the CMB, patterns in the distribution of galaxies, or unexpected behavior in fundamental constants could point to interactions with other universes or evidence of their existence. Future missions, such as those designed to probe the early universe or detect primordial gravitational waves, may provide further insights. Simulations and theoretical models also play a crucial role in exploring the implications of the multiverse. By studying how cosmic structures form under different physical conditions, scientists can better understand the diversity of possible universes and refine predictions about our own. These models bridge the gap between abstract theory and observable phenomena, offering a way to connect the multiverse to the structures we see. The multiverse represents one of the most ambitious and speculative ideas in cosmology, pushing the boundaries of science and philosophy. It challenges us to expand our perspective, to consider the possibility that the universe we inhabit is just one of countless others, each with its own story and structure. Whether or not the multiverse exists, exploring its implications deepens our understanding of the cosmos and inspires us to seek answers to the ultimate questions about reality and existence. In contemplating the multiverse, we confront the vastness of possibility, a reminder that the cosmos is far more complex and mysterious than we can fully comprehend. It is a testament to the power of human imagination and inquiry, a journey into the unknown that reshapes our understanding of the universe and our place within it. Black holes, the enigmatic objects formed from the collapse of massive stars or the accumulation of vast amounts of matter, are among the most powerful and influential entities in the universe. While they are often perceived as cosmic devourers, their role in shaping the universe's largest structures goes far beyond destruction. From regulating galaxy growth to influencing the formation of clusters and even larger features, black holes are critical architects of the cosmos. At the heart of most galaxies, including our Milky Way, lies a supermassive black hole, SMBH, with masses ranging from millions to billions of times the mass of the Sun. These black holes exert immense gravitational forces, anchoring their host galaxies and influencing the motion of stars, gas, and dark matter within the galactic core. Their formation and growth are deeply intertwined with the evolution of their host galaxies, creating a feedback loop that shapes structure on multiple scales. The relationship between supermassive black holes and their host galaxies is encapsulated in the M-sigma relation, which links the mass of a galaxy's central black hole to the velocity dispersion of its stars. This correlation suggests a close connection between black hole growth and galaxy formation. As galaxies evolve, the accretion of gas and mergers feed their central black holes, causing them to grow in tandem with the galaxy. One of the most dramatic ways black holes influence structure formation is through active galactic nuclei, AGN, periods when a black hole accretes matter at an extraordinary rate. As gas spirals into the black hole, it forms an accretion disk that becomes extremely hot and luminous, emitting powerful radiation across the electromagnetic spectrum. This energy output, which can outshine the combined light of the galaxy's stars, drives winds and jets that extend far beyond the galaxy's core. AGN feedback plays a pivotal role in regulating galaxy growth. The energy released by AGN heats the surrounding gas, preventing it from cooling and collapsing to form new stars. In some cases, powerful jets from the black hole eject gas entirely, depleting the galaxy of the material needed for star formation. This feedback mechanism helps explain why many massive galaxies in the universe are no longer forming stars, as their gas has been effectively quenched by their central black holes. Black holes also influence the larger-scale structures of the universe, particularly in galaxy clusters. In the densest regions of the cosmic web, clusters of galaxies are held together by gravity, with a hot intercluster medium, ICM, of gas filling the space between galaxies. Supermassive black holes in the cores of these clusters release energy through AGN activity, creating bubbles, shocks, and sound waves in the ICM. These processes redistribute energy within the cluster, preventing gas from cooling and forming stars, and shaping the overall dynamics of the cluster. The presence of black holes can also be detected through gravitational lensing, a phenomenon where the immense gravity of a black hole bends the light of background objects. This effect not only provides direct evidence for the existence of black holes, but also allows scientists to map their influence on surrounding matter. In some cases, gravitational lensing has revealed the presence of intermediate mass black holes, bridging the gap between stellar mass black holes and supermassive ones. The role of black holes in structure formation extends to the cosmic web itself. Simulations of cosmic evolution, such as the illustrious TNG project, show that black holes play a crucial role in regulating the flow of gas along filaments and into galaxies. By heating and expelling gas, black holes can alter the density and temperature of the intergalactic medium, influencing the growth of galaxies and clusters within the web. The formation of black holes, particularly supermassive ones, remains one of the great mysteries of astrophysics. How did these objects grow so large so quickly in the early universe? Observations of quasars, luminous AGN powered by supermassive black holes, have revealed objects with billions of solar masses less than a billion years after the Big Bang. This rapid growth challenges current models of black hole formation and suggests the existence of seed black holes formed through exotic processes, such as the direct collapse of massive gas clouds. In addition to supermassive black holes, smaller stellar mass black holes also play a role in structure formation. These objects, formed from the collapse of massive stars, contribute to the enrichment of the interstellar medium with heavy elements. When they merge, they produce gravitational waves, ripples in space-time that propagate across the universe. Observations of gravitational waves by LIGO and Virgo have revealed populations of merging black holes, providing insights into their formation and distribution. Black holes are not static entities. They evolve over time, growing through accretion and mergers. As galaxies collide and merge, their central black holes are drawn together, forming binary systems. These systems eventually coalesce, releasing gravitational waves that carry information about their masses, spins, and orbits. The study of these events offers a unique window into the role of black holes in shaping cosmic structures. In the distant future, as the universe continues to expand and star formation dwindles, black holes will remain as some of the last active objects in the cosmos. Their influence on structure formation will wane, but their legacy will persist in the galaxies, clusters, and cosmic web they helped shape. Black holes are more than cosmic anomalies. They are central players in the drama of the universe's evolution. Their immense gravitational pull, energy output, and interactions with matter create a profound and lasting impact on structures ranging from galaxies to the largest scales of the cosmic web. By studying black holes, we not only uncover the mechanics of these mysterious objects, but also gain a deeper understanding of the forces that have shaped the universe itself. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.